Robert, are you there? Mail parties. Saurabh
Raichaudhuri, can you hear?
Yeah, I'm here. Shall I share my screen?
Please.
Is my screen visible?
Yes. You have to open
Yeah.
make it full.
Is it fine now?
Okay, fine.
Okay. असुविधा नहीं. ठीक है. हाँ, ठीक है. Probably still there is 5 minutes. So
Yeah. You people just tell me, then I will start accordingly.
yes, sure. Maybe not. So welcome back. Good afternoon, everyone. So now have the first talk after the lunch break. First talk, the speaker now is Gaurav Rai. I will be talking on non-abelian dual of Tensionless Limits. So this is a contributor talk for 20 minutes. Gaurav.
Yes. Okay. First, I would like to thank the FTGP organizers to give me the opportunity to present my work in the beautiful conference. So here is the title of my talk, the non-abelian T-dual of Tensionless background and Tensionless limit. So first, I will talk about a kind of motivation and outline of our work, followed by some technical details. I won't be able to go through all details due to the time constraint. But however, I will talk about some outline about the non-abelian T-duality. There is kind of new T-duality. And then actually I will enter the core part of our work. And then actually I will talk about some conclusions, ongoing work, and so forth. So, okay, let's start. Okay. So now the plane wave spacetimes, in shorthand is known as a PP wave spacetime. And why it is important? Important in the context of the string theory. Because as we know, the PP wave admits actually the all curvature invariant. One can construct from the PP wave background, starting from the even scalar or up to some derivative of the Ricci tensor. So whatever scalar you can construct for the PP wave background is actually identically vanishes. So it actually leads to there is no alpha prime corrections for the PP wave background in the context of the string theory. Not only that, they actually PP wave doesn't provide any GS correction also. So it is in the context of the string theory why it is interesting, because it provides an exact string background. We know in the string theory picture, there is only some background provides the exact string background, and the PPA is one of them, so it provides the exact string background. Okay. Now the famous Cft correspondence introduced by Maldacena in 1997. So one can construct the interesting string state in the context of the PPA geometry. Via Cft correspondence, one can construct the interesting string states from the guest theory perspective. Okay. Now there exists a precise Cft correspondence in the context of the PPA geometry. So if you quantize the closed strings moving in the PPA background, so upon quantization, you will get some modes, string modes. These are the closed string modes. And actually the three peoples, Bernstein, Maldacena, and Nastase, maybe third one is in the audience. So anyway, so there is a precise correspondence. Exit upon quantization, you will get some closed string modes. And it turns out that this mode is actually one-to-one correspondence with the set of operators in the dual guest theory. It is not a full guest theory in the context of the PPA. It is actually, you are actually confining yourself at a certain sector of the dual guest theory. Okay. Now after BMN introduced his famous BMN correspondence, this is known as the BMN correspondence. So in the 2002, when BMN introduced this famous BMN correspondence, then after the decades, the other people actually investigate the BMN picture, means the PPA BMN operators in the certain type 2B backgrounds, which is for the maximally supersymmetric. This is actually work carried out the BMN, and there's actually follow-up work where people trying to investigate some BMN PPA in the type 2B compactifications, like the Cleft-Witten background. This is the least supersymmetric case, and as well, so far there are some fractional brain backgrounds, and so far so on. Okay. However, recently, actually not recently, some 10 years back, actually now people have turned on interest to investigate the PPAs, BMN in type 2A backgrounds. However, is in the string theory, in the context of the string theory, this type 2A background is not like it's something new background. It's not like that. However, this type 2A background is actually the T-dual of those type 2A backgrounds where BMN is already studied, and it is actually well understood. However, if you people remember, the T-dual business is actually initiated by Buscher in 1990, and follow-up work by Hassan. So if you have some string compactifications which admit some U1 isometry, so there are some some formalism introduced by Buscher and Hassan. You can construct it somehow is some equivalent background of it. However, actually the group of Swansea people is 10 years back, the group of Swansea people, they actually generalize isometry. These people actually generalize those Buscher rule for the non-abelian isometry. As like you have some background which admits some rich isometry. Rich isometry in the sense you have some non-abelian isometry like SO2, SO3, whatever. So by actually mimicking the work of the Buscher and Hassan, one can construct its equivalent background. And this is actually the kind of non-abelian T-duality. However, there is actually many more differences if you compare the non-abelian T-duality with its abelian counterpart. First of all, the non-abelian T-duality is a symmetry at the low energy excitation of the string theory. So as we know, the famous work by Verlinde and Ashok Sen, that abelian T-duality is actually a symmetry of the full string background. However, the non-abelian T-duality is just a symmetry of the low energy excitations. So if you confine yourself, or if you just concentrate your attention in the supergravity level, so it behaves well in the supergravity level. So now the string theory people can ask obvious questions, that if it is not a symmetry of a full string background, then why will take care about the non-abelian T-duality? Okay, so best answer is so by applying the non-abelian T-duality, one can construct new supergravity background which actually correspond to new CFT duals. This CFT dual is completely different from the seed CFT duals. Okay, sorry. Now the question actually this Swansea people asks, although it is not a symmetry of the full string, the full alpha prime order, however, this non-abelian T-duality provides any PPA background which is an exact string background. So thus these non-abelian T-dual solutions provide any PPA backgrounds or not. Okay. So along the line of their investigation, they actually considered the non-abelian T-dual of ADS5S5. This is the famous Maldacena background, and they actually showed that non-abelian T-dual of this type 2B compactification, which is maximally supersymmetric. So this non-abelian T-dual solution indeed admit PPF geometry. However, motivated by their work, in our previous work, we actually considered the Klebner-Witten background, and we also showed that non-abelian compactification of the least supersymmetric background because it is n equal to 1 supersymmetric. So this supersymmetric and the least supersymmetric background is actually also admit the PPF geometry.
Excuse me.
Yes.
Excuse me, Shurab.
Yes.
Why is it that the massive modes of the string, right, do not have this property of non-abelian duality? Can you say that in a minute?
Because first of all, during if you remember the Busher rule for the abelian one, it preserved the symmetry.
No, I don't. Can you tell me what that rule is? I mean, I'm not doing string theory, so what's the physics reason? You have massive modes, right, in the string theory, which apparently do not obey the non-abelian T duality. Is that correct as a statement?
Yeah. Yes.
Yeah.
Because
So
during
my question is why?
Yeah, because during dualization you lost the symmetry.
During the realization, you lost the symmetry.
During the non-abelian T dualization, you lost the symmetry. So in the seed background, whatever you start from the seed background, you have some symmetry. In the dualized background, you lost the symmetry.
So the dualization does not treat the masses in the same way for some reason.
No.
Okay.
I will come. What does mean by actually come? I will in a minute. Yeah. Shall I proceed?
Please.
Okay.
Thank you.
Yeah. Okay. So now there is actually a series of n equal to 1 backgrounds. The starting from the Klebner-Witten there is actually some invariant RG flow starting from the Klebner-Witten fixed point, end up with the Klebner-Settler. So there is a RG flow from Klebner-Witten fixed point, then Klebner-Settling, which is actually non-conformal backgrounds, and then end up with the Klebner-Stassler. However, so this background is kind of towards the realistic models. So anybody actually will object why it is a realistic model. I'm not saying it is the realistic model. I'm saying that it is towards the realistic models. In that sense, these are the least supersymmetric. So these are the n equal to 1 supersymmetric. However, it turns out that their dual backgrounds, the non-abelian dual backgrounds, is also least supersymmetric, means it is also n equal to 1 supersymmetric. So now, as we in our previous work, we actually investigate the PPF solutions in the Klebner-Witten background. So now, in the present context, we actually investigate is the Klebner-Settling background, the T dual of Klebner-Settling background provides any PPF geometry or not. Okay. So now actually this is more or less outlined. First I will talk about some non-abelian T duality. I won't go to the technical mathematical details. It will take a few hours if I start all these things. And then actually I briefly mention about the Penrose limit, followed by the sheet background, this type 2B compactifications and its dual. And then actually I show the core part of our work, which is the Penrose limits in the dualized backgrounds. And if time permits, then I talk about some dual field theory. However, it is not so understandable, not only about this context, this all actually some open directions to study the CFT duals for these non-abelian backgrounds. And then actually I will advertise some our ongoing works, and there are some future directions. Okay. So just as I told that non-abelian T duality is actually generalization of the Busher rule, which are the famous T duals famous rules invented by the Busher in order to carry out the T dual business starting from the type 2B background, which admits some U1 isometry. So non-abelian duality is actually generalizations of the Busher rules. So just as a quick recap for the Busher rule for the abelian one, we know that there is actually the 3-step recipe. We start from a sigma model actions, which is known as a PCM action and then actually we gauge the global isometry by introducing the gauge field. So actually we evolve the global isometry to the local one, and then actually we introduce some Lagrangian multiplier in order to invoke the flat connections in the worldsheet Lagrangian, and then actually we integrate out the gauge fields, and the Lagrangian multiplier behaves as a coordinate in the T dual sector. So this is actually more or less outlines of the Busher work for the famous for the abelian one. So non-abelian one is actually the mimicking this procedure, the 3-step procedure. However, there are some certain differences because the gauge fields where you introduce for the non-abelian case is actually the gauge fields is actually some group valued. So it is a group valued gauge field. Sorry. However, as I mentioned, this non-abelian dualization is actually the solution generating technique, because during dualization is just loss isometry. So it is just a solution generating technique in the supergravity level. It is not a symmetry for the all alpha prime order in the string theory. However, as I think Professor Parthasarathi was asking, that if you remember the Boucher rules for the abelian one, is just if you start from a U1 isometry in your dualized background, there will be an U1 isometry. However, the non-abelian 2 duality doesn't do that. I am not saying that I start from some S3 manifolds, I have some big S3 manifold, it will end up with some small S3 manifold, something not like that. However, it maps from one vacua in the supergravity, it maps from one vacua to another vacua. Okay, so now, so this actually, and the dualization procedure, the isometry of the original background is actually destroyed. What does mean by partially? That will come when I talk about one example. Okay. Not about that, as I mentioned, it is not a symmetry of the alpha, all order of alpha prime. However, people still today, people don't know how to address the non-abelian T-duality in the context of the GS correction. The topological corrections, we don't know how to even address the topological issue in the context of the non-abelian T-duality. There are some remedy about the alpha prime issues, which is context of the double field theory, but in GS correction, we don't even know how to talk about the GS corrections in the T-dual business. Okay. However, it turns out that by the actually Swansea people in their paper, they actually explicitly shown that if you consider the T-dual of ADS5 S5, which is actually type 2 Sugra solutions, and if you consider the M lift of their solution, it is very close to the GM geometry. Okay. So roughly in one sentence, the T-dual business is actually the NS sector is completely defined. The NS sector is completely worked out by gauging the sigma models, starting from the PCM actions, and RS sector, the construction of RS sector is based on how T-duality is actually rotates the Clifford space, which is actually the basics of the RS sector, which is the basis actually the spinors of the RS sector. Okay. So now, this actually Swansea people over there actually 10-20 papers. They investigate the various, they investigate the non-abelian T-duality for various type 2 backgrounds like ADS5, ADS4, whatever be. And they actually in their paper, they actually talk the details construction of it. I'm not going to the details. I'm just closing these sections by talking about one example. And here is the example. The simplest case, I'm considering the near horizon geometry of D1, D5 systems. So the geometry is governed by some ADS3, S3, T4, and there's completely disjoint part in the metric. And the RS sector is actually just contained by the F3, which is actually effectively the volume of the S3. Okay. So now the S3 manifolds is actually indicates the global isometry SO4, which actually can be right in some SO2 left into SO2 right. And in order to construct the T-dual solution, we are only focusing the SO2L part. Now the Swansea people is actually work out the T-dual solutions, and this is the T-dual solution. So ADS3 and T4 behave as a spectacular part during the dualizations. However, the dualizations on S3 actually give some apparent non-compared directions. Why it is apparent, this is actually a long story. However, this you can consider there is some non-compared directions, and this partially that I mentioned that we lost the isometry partially. So SU2L actually we have lost. However, the SU2R is actually reflect in the S2 in the S2 part in the dualized sector. Okay. Now is actually the dualized background. If you just consider the dualized part of the S3 is actually interpolates between R3 and R cross S2. However, this background is actually supported by the two form, by the Clapeyron 2 form and the dilaton in the NS sector, and the RS sector we have all fluxes. All fluxes means the F0, F2, and F4. So due to the presence of the F0, it is a massive type 2 backgrounds, which is n equal to 1 supersymmetry. This background is actually n equal to 1 supersymmetry. Okay. So now actually I briefly mentioned the Penrose limit. So here is the Penrose limit means if you start from a background means if you have a line element or even some metric, and you choice of the null geodesic such that if you expand your background around the null geodesic, you will end up the plane wave metric. So mainly if you start from a background which admits some null geodesics, this null geodesic should be smooth, means there is no like they are not singular null geodesics, they are smooth null geodesics. And if you expand the background metric around the null geodesics, you will end up with the PPA metric. This is actually the Penrose theorem. Okay, now so just as a quick recap, so the quick review. So you just consider the geodesic equation. This is my geodesic equations, and U is some affine parameter along the geodesic equations. And if you consider the motion, now I'm considering the motion of a particle with very high speed, means some isometric direction. Don't mix this isometry with no abelian, non-abelian. This is completely different. So if you consider the motion of a particles about some isometric directions, so your geodesic equation boils down to these expressions. However, I am considering the motion of a very high speed, so it is actually so it will obey the null geodesic conditions, which is given by here. Okay. So now, so now actually I am talking about some core part of our work. So now, as we know, the famous area Cft correspondence introduced by Mallasena, which is actually the duality between the string in nature in radius 5s5 with the operators in the boundary n equal to 4 superangles theory. And actually, after introducing Mallasena, people were trying to investigate what are the gravity duals of 4-dimensional Cft. And next work is actually carried out by Klebner and Witten by introducing ND3 banes at conical singularity, which is actually the gravitational background is equivalent to gravitational background of radius 5T11, which is yes.
You have 3 more minutes.
Oh, sorry. Okay, so these are the backgrounds, which actually then actually one step further, Klebner said didn't go, and this is actually the SUN plus SUN guess theory. However, and this is the gravitational background. The gravitational background is singular because there is some log factor is playing around. So this background is actually some type 2B solutions with the F3 and F5 in NS sector and B2 and the NS sector. And this background supports some SU2 isometry. And people actually dualize this background. This is quite complicated. Dualized solution is quite complicated. However, there is some isometry along this direction. There are some certain directions in the dualized background. So we actually consider this. So this actually completely this is the full solutions in the dual sector. However, this is a quite complicated background, the singular background. And there are some isometries in the dual background, some psi and phi 1 directions. And we actually, okay, so this is the T-dual background is actually B2 and phi in a sector, and all fluxes are present in the other sector. And this actually also the massive type 2A solution, which preserve the n equal to 1 supersymmetry. And these 2 directions is actually the isometric directions. So we actually investigate the Penrose limits in these directions. And these are the procedures. First, we consider the psi directions. However, the psi and pi direction separately. However, it doesn't give to the any PPO geometry because the geodesics are singular. However, there is one geodesics admit in the T-dualized geometry, which leads to PPO geometry. And this is the PPF solutions in our context. So there is some singularity presence at r equal to r tilde, and this is the signature of the singularity of the original background. Okay. So now there are some notions about usual things in order to express the PPFs in the Bigman form. So these are the PPF in the Bigman form. Apparently, it looks like there is a smooth geometry. However, this singularity are hidden in the expression of Fi. So these are actually known as the Bigman mass, and the singularity are hidden in the expression of the F5s. Okay. So now we explicitly checks all the type 2A equation of motions. Bianchi identities is satisfied so our PPF solution is indeed a type 2A supergravity solutions with preserve the n equal to supersymmetry. There are some enhancement in the supersymmetry. There is some enhancement at the Penrose limit, and the Einstein equation is actually fixed some null geodesic some coefficients of the Penrose limit expansions. Okay, so shall I stop here or?
Yes, I think Saurabh, your time is just up. So
okay, so
then just come to your summary.
Oh yeah, sure. So actually, the dual background is not so well understood. However, the dual background for the original case is just actually the one can describe the original solution, background in the context of the D3 and D5 brane. And actually, the main goal of the investigate the non-abelian dual is actually if you consider the Bonnet-Friend actions in the original theory, and if actually consider the same actions in the T-dual theory is match up to constant factor, the effective tensions, one can actually work out the holographic central charge and integral entropy. However, it actually doesn't give any new insights to order to examine the gauge theory dual for the non-abelian T-dual case. However, it turns out that if you consider the gauge coupling analysis by integrating the B2 in some cycles, it gives some strange behavior. And however, one can actually work out the brane charge, various brane charge in the original and T-dual background, and there are some relations. It turns out that some brane mapping one can do from seed background to the T-dualized background. And as we know, there is some cyber duality presence in the original background in terms of the D2, D3 brane. The similar phenomenon can be observed in the D5 in the dual sector in terms of the D6 brane. However, still the Q-bar theory for the non-abelian dual is still missing. Okay, so now one can do.
I think your time is up. So
yeah, okay. So then okay. So then actually we started in our work. We started the non-abelian T-dual of Klepp-Newton backgrounds, and it provides some new supergravity solution. We consider the null geodesics. One geodesics actually admits some PPF geometry. And okay, so I'm not going to these sections. However, actually we couldn't identify the proper BMN sectors in the gauge theory, and it is actually, so there is some further investigation needed in order to identify the BMN sector. Okay, so in moving work, we are trying to explore the Penrose limit in the non-abelian T-dual of ADS3 backgrounds, and there are some holographic entanglement issues are there in the PPF geometry that we are trying to explore. And these are some key references of my work. And okay, I stop here.
okay, so thank you very much, Saurabh, for a nice talk. So let's time for questions maybe from the first in the audience and also in online mode. Maybe a couple of questions. So there are no more questions. So let's thank the speaker once again. And the next speaker is Robert Dimilakov. He's
just
he's from Understand Institute for Theoretical Physics, the University of Witwatersrand, Johannesburg, South Africa. So we shall be talking on bilocal holography. It's an invited talk for 40 minutes. So Robert, can share.
Can you see my screen? Can you hear me?
Yeah, I can hear you, but we still cannot see your slides.
Okay, so let's see.
So you have to click on the present now option.
Can you see my screen?
No, sir.
It is still not visible.
Yes, sir. It's coming.
Yeah, it is coming.
Okay, very good. Okay,
So Robert, it's all yours.
okay, great, thank you. So thanks very much for this invitation to speak at this very interesting meeting. Let me say that I've enjoyed the first day very much so far. So I will be talking about basically bilocal holography. And to give you an idea, what is bilocal holography? The idea is we want to pursue a constructive approach towards holography. So what I mean by that is if you are given the CFT, the field theory, how would you actually construct the dual gravitational description? And I'm going to try to give you or motivate a recipe and show you that it works in some simple cases. If anybody has any questions, please, you're very welcome to ask as I carry on.
I do have a comment. Could you please go to the full screen mode? Because the things
okay, I don't want to go to full screen mode because for some reason my laptop is freezing when I do that.
Okay, sorry.
No problem. Okay. So here are some references. The first reference here is where the idea first appeared, a paper by Dasenjevitsky, now almost 20 years old. Then the second paper that I've listed is a paper that's about 10 years old now, and that's where we first gave a concrete example of how this works. And this most recent paper is what I'll be talking mainly about. And here is where I try to explain something about how bilocal holography is working. Okay, so let me just motivate this a little bit. So we know by now there's very good evidence that you can describe quantum gravity in negatively curved spacetime, so ADS spacetimes, in terms of a set of degrees of freedom of a conformal field theory that lives on the boundary of that ADS space. The initial example that was proposed and most well-studied example relates n is equal to 4 super Yang-Mills theory to 2B string theory on ADS5 spacetime. Now, although there's a lot of evidence for this example, it's hard to prove it. And basically, the conformal field theory is difficult. It's a multi-matrix model, so the dynamics of that is not well understood. We know some things, but we certainly don't have a complete understanding of the CFT. And as far as the dual gravitational theory goes, we don't really have a good non-perturbative definition, independent definition of 2B string theory on ADS5. So in an attempt to find perhaps a simpler example to study, I'm going to be studying the duality between the free ON vector model and higher spin gravity. And in this case, the higher spin gravity still is not well understood. And at quantum level, not a lot is known about the theory. But at least on the CFT side, the ON vector model is well understood, and we can calculate pretty much anything that we're interested in. So what is this free ON vector model? Well, there's the action of the theory. So it lives in 2+1 dimensions. It's simply a massless field, and you've got n copies of the massless field. The ON symmetry is a gauge symmetry, so your physical observables would be gauge invariants. And just in analogy to the language from matrix models, the invariant here would be phi A with the index A contracted. And because you've got a single sum over color, I'm going to call this a single trace operator. That's the language that we usually use. There's no trace here, but we just call this a single trace operator. If you're studying gauge gravity duality, it's the spectrum of single trace primary operators that tell you what is the field content of the dual gravitational theory. For this free CFT, it's quite easy to work out what are the single trace primaries. So the first one is O delta is equal to 1. This is a scalar operator with dimension 1. And then we have a family of conserved currents. There's one conserved current for every even integer spin. And these primaries are given by essentially taking a weighted sum of derivatives of the two scalar fields, as shown in the formula at the bottom of the slide. So that's the complete spectrum of single trace primaries. What we would expect from the spectrum is that the dual gravity theory has to have a bulk scalar corresponding to O delta is equal to 1, and a gauge field corresponding to the conserved currents. So there'll be a gauge field for each spin, 2, 4, 6, 8, and so on. So is there such a theory? In fact, Vasiliev has written down a set of equations. They are nonlinear, they're gauge invariant, and they should describe higher spin gravity. These equations admit a vacuum solution, which is the ADS spacetime. And in the simplest bosonic 4D theory that Vasiliev wrote down, the theory is a theory of a scalar and a set of massless higher spin fields, and the spins of these fields are 2, 4, 6, 8, and so on. So the field content exactly matches what we would expect for the dual of the ON vector model. And in fact, it's been proposed that this Vasiliev theory in 4D is dual to the 2+1 dimensional vector model. We don't know the full quantum theory. And in fact, we don't even know how to write down an action that reproduces Vasilyev's equations. So at this stage, the gravitational theory is certainly not defined, and there's a lot that we don't know about it. But starting from these classical equations, we can do a few things. So we're going to work out what are the free equations of motion following in Vasilyev's theory. These free equations of motion should correspond to the strict large N limit of the Owen vector model. We're going to work in the light cone gauge, and we're going to completely gauge fix the theory. So we're only working with physical theories, physical degrees of freedom. And this makes sense because in the vector model, we are working with gauge invariance. So there too, we only have physical degrees of freedom. I'm going to follow Meta here. Yes.
Sorry for the interruption. I'm just curious. Are the Vasilyev equations just free field equations for the high spin fields, or do they involve couplings?
No, in fact, the Vasilyev equations are interacting equations. They're written in terms of auxiliary fields and physical fields, and it's a nonlinear set of equations. The reason why we think that these equations are promising and make sense is that they have a complete higher spin gauge symmetry. But you know, as I was saying, I mean, I think that it's fair to say that this theory is still in its infancy. But it's a unique set of equations with interactions and that set of higher spin gauge fields.
Thank you very much.
Okay, so we're going to work in Poincare patch of ADS4 and with a light cone gauge fixing. So I'm going to take Poincare coordinates x0 and x2 and combine them to give me x plus and x minus. x1 I'm simply going to call x, and z here, the z coordinate, is the radial coordinate of the ADS space. So that's the extra dimension that is meant to somehow emerge holographically. In light cone gauge, we set components of the gauge field equal to 0 as with one or more plus polarizations. So even just one plus polarization, you set that gauge field component to 0. Once you've done that, you have to impose the constraint that comes from the equation of motion associated to this field. And that tells you that the gauge fields with one or more minus polarizations are determined. So in the end, after you've done this gauge fixing, and you do it for all spins, the dynamical fields are just the XZ polarizations of this gauge field. The free equation of motion for this gauge field looks like just a free massless wave equation. And the fact that the equation is so simple and looks the same for all spins is peculiar to the case of ADS4. In other dimensions, you wouldn't find such a simple result. Please remember that equation of motion because I'm going to compare to that later. Okay, so what is bilocal holography? So here is the basic claim. So holography, so extracting the gravitational theory from the conformal field theory is accomplished by doing two things. First, you make a change of field variables. So I'm not going to work with the original field phi A. I'm going to introduce a new field, a bilocal field. The second thing that I'm going to do is I'm going to change coordinates in the CFT. And that's the space-time coordinates. And I'm going to change coordinates so that I give a bulk interpretation for the bilocal theory. I'm essentially going to tell you how the points in the ADS4 bulk correspond to points in the conformal field theory. I now want to motivate why these two steps are needed and why this corresponds to holography. So the first thing is, when written in terms of the original field variables, the loop expansion parameter of the conformal field theory is h bar. After you perform the field change of variables, the loop expansion parameter is 1 over n, and that maps the loop expansion parameter expected of the dual gravity. So why do we need to perform the field change of variables? This rearrangement of the dynamics takes a loop expansion with parameter h bar to a loop expansion with parameter 1 over n. So that's what we expect for holography. Now, why do we perform a change of coordinates in the field theory? Well, the basic field phi a transforms in a representation of the conformal group of dimension 1/2 and spin 0. Our invariant fields is going to be phi a contracted with phi a. And what that means is this bilocal field phi a will transform in a tensor product of the 1/2 naught representation with itself. That is a reducible, that tensor product is a reducible representation. And if you work out what representations appear, you have a representation of dimension 1 and spin 0, and then you have an infinite sequence of representations. They have dimension s plus 1 and spin s, where s is any even integer. So what you can see is the representations appearing on the right-hand side of equation 5 corresponds exactly to the spectrum of fields in the higher spin gravity. So we want to change basis. We want to change from a basis for the Lie algebra, which corresponds to the left-hand side of equation 5. That's where you start in the CFT. We want to change basis to get something that looks like the right-hand side of equation 5, because that's the basis which looks very natural from the point of view of the higher spin fields. And I'm going to show you the change of coordinates that does that. Okay, so now let me explain these 2 points. So if you want to solve quantum field theory, all you need to do is evaluate some complicated integral. So this is the Feynman path integral. Well, I've put all in inverted commas because you're not performing one integral. You have to perform n integrals. It's over each phi a. And we're taking the limit that n goes to infinity. It looks like a very complicated problem. And in fact, in most cases, this would be hopelessly difficult. But things simplify a lot if you have an ON symmetry. If you have an ON symmetry, it means the action has to be an ON invariant. And so if phi a would be in the vector representation of ON, then you know that the action has to be a function of sigma, which is the contraction of phi a with phi a. If you now change integration variable to integrating over sigma, the integral over the orthogonal directions to sigma are all trivial because you actually don't depend on those directions. Then you'll end up having to do just a single integral, the integral over sigma, as shown in equation 7. What is noteworthy is that the exponent comes multiplied by a factor of n, and that always happens basically because we had a total of n variables. But that n sitting in the exponent is crucial because it means if you now perform a saddle point evaluation of equation 7, you're naturally going to get a loop expansion with parameter 1 over n as the loop counting parameter. Now, sorry, let me just do one thing because I guess. Okay, good. For our CFT, we're working in 2 + 1 dimensional Minkowski space. I'm also going to use light cone coordinates in the Minkowski space. So I combine x0 and x2 to give me x plus and x minus. And then x1 I'm again just going to call x. Our bilocal field is obtained by contracting 2 phi fields. They're at the same time x plus. So I'm going to do an equal x plus quantization. But my first field depends on points x1 minus and x1. My second field, x2 minus and x2. And in that sense, it's bilocal. It depends on 2 points in space. So my field sigma depends on time, x plus, and then 2 points, x1 minus x1 and x2 minus x2. So a total of 5 coordinates. Good. Okay, now, the field.
Oh, sorry, interruption again. Is this a kind of point splitting you're doing?
No, so I'm normally going to have the 2 phi's well separated from each other. And I'm going to work out the large N value for what this expectation value of sigma is. But after that, you can imagine the actual dynamical field is something that's normal ordered. So there's not going to be any singularities when these 2 points approach each other. The reason why I've got these 2 points appearing, or why there's 2 fields appearing, is actually being driven by the gauge invariance of the theory. So when I've got phi A summed over A, this is a gauge invariant operator. So this would be something that would correspond to a physical degree of freedom. So that's really the motivation.
But when you have bilocal fields, then the gauge invariance, there must be a Wilson line connecting the 2 points, right?
Okay, very good. So indeed, if I had so I'm right now saying there's ON symmetry, and I'm simply declaring that it's a symmetry. There's no gauge field here. And what that amounts to doing is to saying that inside my Hilbert space, I only keep the singlet sector. Now, you might wonder, is this a sensible thing to do? Well, one thing that you could do, you could couple this theory to a gauge field, and in 2+1 dimensions, you could couple to something like a Chern-Simons gauge field, and then you really could give a Wilson line construction. So you make this bilocal gauge invariant in that way, and then you can take the level large enough that the gauge field is not dynamical. So I'm just taking a more pedestrian approach here.
Okay, great, thanks.
Sure. Okay, so now this field sigma itself develops a large N expectation value. So if I look at what does sigma look like, sigma is equal to sigma naught, and then there'll be some fluctuation, 1 over square root N times eta. Sigma naught is nothing but the large N 2-point function. So a very simple thing to calculate. Eta is really the dynamical field in the large N limit, and it is eta that we are going to try to identify with the higher spin fields. So that's the takeaway point so far. Eta is what we're going to identify with the higher spin fields, and the loop expansion parameter written in terms of the field eta has 1 over N as the loop counting parameter. Okay, so now let me tell you the change of space-time coordinates that I'm going to do. So we have an infinite number of spinning fields. So we would have coordinates x plus, x minus, x, and z in ADS4. And we would have the gauge fields and an infinite number of them, and then the bulk scalar. I'm going to think about this slightly differently. So I'm going to introduce one more coordinate, theta. It's not a geometrical coordinate. It's a bookkeeping device. If you look at my metric, that's still the metric of ADS4. So I'm not thinking of theta as being geometrical at all. But using theta, I'm going to repackage all of my higher spin fields into a single field that now depends also on theta. And if you want to extract any particular higher spin field, you would do some Fourier decomposition, and the coefficient of cos 2s theta in this decomposition would tell you about the gauge field with spin 2s. And in a few slides, I'll spell out precisely what is the relation between phi 2s and the spinning gauge field. Okay. So what is this change of coordinates, the space-time coordinates, meant to accomplish? Well, the bilocal transforms in the v1/2, naught tensor v1/2, naught representation. So if you were to act with any element of the conformal group, the action is just through the usual coproduct. So you would have the generator acting on the first field, leaving the second alone, plus leave the first field alone and act on the second. So this I'm going to call this action LA, and I've got a little tensor as a subscript to remind you that this is the tensor product action, the usual coproduct action. But what we know is, and look at the equation 11, on the left-hand side, we've got the language that's familiar for the conformal field theory. On the right-hand side, this is the language that is familiar for the ADS space, the higher spin gravity. And each representation on the right-hand side of equation 11 corresponds to a different higher spin field, and every higher spin field is represented on the right-hand side. So we would like to change our basis from the left-hand side of equation 11 to the right-hand side of equation 11. What do I mean by the right-hand side? Well, if I was to act with an element of the conformal group on this field phi, I would want the action of the conformal group to correctly give me the action on the representation of spin 2s and dimension 2s plus 1, as I've shown in this equation. So that's the action that we're looking for. And so how do we achieve that? In fact, it can be achieved by a simple change of coordinates. To write the coordinates down, it's simplest to do the following. We know that there is a symmetry in the gravity under shifts of x minus and a symmetry in the CFT under shifts of x minus. So I'm going to Fourier transform on the x minus variable. Fourier transforming x minus, I replace it with p plus. So the bilocal now has coordinates little x plus, little x1, little x2, little p1 plus, little p2 plus. So those are the 5 coordinates of the bilocal in the CFT. In the ADS space, I've got x plus, the light cone time of ADS, and I'm identifying that with the CFT light cone time. And then I've got capital X, I've got capital P plus, which is conjugate to x minus, I've got Z, which is the radial direction, and this angle theta. This change of coordinates, which can be inverted, there I've given you the inverse, it in fact allows you to map the tensor product representation on eta into a direct sum representation on phi, and phi is now just given by 2 pi p plus sine theta onto eta. And you can prove, in fact, that this is the unique mapping that will do it. So this field capital phi now really is transforming in the correct way under the ADS isometries to be identified with the higher spin gravity fields. The whole construction so far has only used the SO23 symmetry of the problem. We didn't use gravity in any way at all. Let me just summarize then what is the construction of the bilocal holography. So our basic field variable is sigma, which is given by this sum over A of phi A. Those are the original fields of the CFT. This then develops a large in expectation value and there's a fluctuation. We then change coordinates as shown in the formulas on red. And this takes us from a set of conformal field theory coordinates to a set of ADS coordinates. And our field phi has got an expansion in terms of theta, and the coefficient of cos 2s theta is related to the gauge field of spin 2s. And I've told you how phi exactly is related to eta. This is all determined by symmetry. Now that we have a higher spin bulk field, we can do some tests. Does this really work? So the first test that we can do, we can ask, are we actually getting a bulk reconstruction? What do we mean by a bulk reconstruction? Well, first of all, the bulk fields, phi, should satisfy the equations of motion that Metsayev derived by gauge fixing the higher spin theory. So do we satisfy the correct equation of motion? Even if we do satisfy the correct equation of motion, that's not enough. We must show that we satisfy the correct boundary condition. And what is the boundary condition in this case? Well, these components phi 2s must reproduce the spinning primary operators of the conformal field theory. So is that the case or not? Well, the first thing that you can do, take the CFT equation of motion that we know, and that implies an equation of motion for the bulk field. And it turns out that the equation of motion that you get for the bulk field is exactly the one that Metsayev wrote down. I'm now introducing an identity, P1 plus P2 plus to the power of S times by the cosine of this quantity is sum. Now to explain to you what is the relevance of that identity, let me just recall something. So the single trace primaries, there's a spinning primary of every even integer spin, is given by this formula. So that you get from CFT by just asking that this is annihilated by the special conformal generator. And this is a very specific sum with coefficients that have a very definite value. Then from our bilocal map, we have a formula for theta. Theta is just 2 times the inverse tangent of the square root of P2 plus over P1 plus. And our bulk field looks like cosine of 2s theta times by this component phi 2s. Important identity that I'm using, oh, I want to have the identity still on the screen. So let me now do that. The identity that I'm going to be using, you can see I've got the cosine of 2s, and then this is just s times by theta. There's my theta, there's my s. And when I work out what this gives me, it gives me, in fact, a sum which is identical to the sum appearing inside the formula for the spinning primaries, with this exactly the same coefficients appearing in the sum as you get appearing in the formula for the spinning primaries. Using that identity, when you go to the boundary of the ADS space, this higher spin field phi s evaluated at z is equal to 0, so that's on the boundary of ADS, the s derivative of this field with respect to x minus exactly reproduces the spinning primary. So the gravity fields, when taken to the boundary, do reproduce all of the primaries of the CFT. And I just want to remind you that this wasn't put in. We didn't use in any way the bulk equation of motion, and we didn't build it in any way to get the correct boundary condition. Our map was built entirely by looking at symmetries. Okay.
Sorry, another interruption. Sorry,
Sure.
another interruption. Does this, well, happy coincidence, I would say, or maybe it's a derivation showing that the boundary conditions are obeyed, the CFT boundary conditions, how far does this depend on your choice of coordinates?
Okay, good. So certainly we have chosen coordinates to map the two sets of generators into each other. That's without a doubt. But for example, one thing that you could have asked, if we do a canonical quantization where we don't quantize with time being x plus, but we just have t, you can perform exactly the same construction. And you also define a map in that case. And if you go to the boundary, you can ask, do you reproduce the set of primaries that you kept in that case? Because you won't be keeping the polarizations that you kept here. You'll be keeping some different polarizations. And in the canonical case, that works out correctly as well.
Okay.
So,
great.
Well, I would say there's some evidence that this doesn't depend on the coordinates.
Okay, great. Thank you.
You know, maybe as another comment, let me just add one other thing. I should perhaps have added a reference here. So when we worked this out, we did it just basically based on symmetry, and then we noticed that this is how the bulk field is related to the primary. One thing that you might be worried about, you might think this looks a bit unusual, because usually the bulk field itself is related to the primary. It's not derivatives of the bulk field that gets related to the primary. So this looks a bit non-local. But in fact, Polchinski and Minton wrote a paper where they showed that using the usual Gupsa, Polyakov, Klebanov, Witten dictionary, in this case, you get precisely the equation that we found. So the equation that just dropped into our lap is what you would get by a more standard holographic analysis. Okay. Now let's talk about subregion duality, another property of this holography. So we can ask what region of the CFT, if any, is dual to a given subregion of the bulk. So to answer this, I'm going to consider CFT excitations. They're at the same time x plus, but I'm going to locate the first excitation at position x1, and I'm going to give it a momentum p1 plus. So I'm imagining a wave packet. It's peaked close to x1, and in momentum space close to p1 plus for these two coordinates. My second excitation, the wave packet will be peaked around x2 and around a momentum p2 plus. Just from our map, just using the map, you find that x and z obey the equation shown in 13. So the bulk excitation is going to be located on a semicircle in the xz plane. It'll have a radius of x1 minus x2 over 2 and a center of x1 plus x2 over 2 and z is equal to 0. So I've drawn a picture of it here. The horizontal line, this is the x direction. That's where the CFT lives. That's the boundary of the ADS space. The z direction, when you move upwards away from this horizontal line, that's when you're moving into the bulk ADS space. The two red dots here are the excitations of the bilocal, and this bulk excitation, wherever it is, sits somewhere on this semicircle. To localize it, you have to pick a certain value for theta. Now, just from this picture, tan theta will be opposite, so z over adjacent, which is x minus x1 plus x2 over 2, and that's the formula that I've written at the bottom here. So this tan theta is z over x minus x1 plus x2 over 2. And if you use the map, plug in what z is, plug in what x is, it turns out that tan theta is nothing but 2 times the square root of p1 plus p2 plus over p1 plus minus p2 plus. And just by manipulating this a little bit using double angle formulas, you can check that this is exactly the theta that we used when we defined our map. So theta is the angle that we introduced as a bookkeeping device. And so that's the picture. This bilocal excitation maps. It's located on the semicircle, and exactly where it's located on the semicircle is determined by theta, which is determined by p2 plus and p1 plus. Okay. So this is starting to look interesting. This horizontal line at the bottom is the CFT. If I pick CFT operators that belong to this red line, I can reconstruct that part of the ADS bulk that lies below this black line. So I can reconstruct bulk operators in this green region. And this whole figure is plotted for a fixed time x plus. So a natural question to ask at this point is, what is the interpretation of this black line? Well, the CFT subregion is, you can have any x minus because we have localized the momentum p plus, but x lies in a strip. So we're looking at a strip of the CFT. In the bulk, we're lying inside some semicircle. So now, we've frozen x plus. So the metric on this x plus is equal to naught slice is given in equation 17. Now I'm going to imagine the following. Let's just consider a region, ER. That region is bounded by z is equal to 0, and we're going to have another curve, z, which is equal to z of x. So the parameter along the second curve is actually the coordinate x. The length of that second curve is what I've shown you in equation 18. If I try to work out what is the curve of extremal length, I get the equation of motion shown in 19. And the solution to that equation of motion is x squared plus z squared is equal to r squared. So what we found is, if we restrict ourselves to this subregion of the CFT, this red line, then in fact, we can reconstruct everything inside this green region. And the black line here is a curve homologous to the red line, but of extremal length. It's got the shortest possible length. This looks a lot like the Ryo-Takayanagi surface. The only difference is that here the Ryo-Takayanagi surface is one-dimensional, described by z of x, but that's a peculiarity of the light cone gauge. When we said x plus is equal to naught, the coordinate x minus is also dropped out of the metric. And what we're learning is, from a boundary region of the CFT, we can reconstruct everything up to this Ryo-Takayanagi-like surface. And that's the usual statement of entanglement wedge reconstruction. Okay, how am I doing with time?
Well, you have 5 minutes now.
About 5 minutes.
Yeah.
Okay, all right. So I think, so let me not rush through this, because so let me rather, I'll just explain two things. So here's the first thing. Let's say you wanted to reconstruct the bulk field at point P. One thing that you could do is you can reconstruct it using the bilocals located in this interval A. And that would be one reconstruction, or you could reconstruct it with the bilocals located inside this interval B. That would give you a different reconstruction. And you know, these really are different reconstructions. If you restricted yourself just to the overlap between region A and region B, you would get this little semicircle shaded in gray. And just from the degrees of freedom lying in this intersection, you cannot even reconstruct the bulk field at point P. Now, this is one of the central statements of quantum error correction, that in fact, depending on which subregion of the CFT you choose to consider, you get different reconstructions of the bulk operator, and it's really being reconstructed in entanglement between degrees of freedom in much the same way that error correcting codes work. We have suggested that our semicircles are related to bit threads that people have used to calculate entropies. We can give a proof of entanglement wedge reconstruction. Let me maybe come now to some future directions. So the first thing that you'd like to know is, can you construct a similar geometric interpretation for the case we perform a canonical quantization of the conformal field theory? Actually, that's something that we're working on now, that hopefully in a matter of months, we will have something to say about that, but it looks like it all works out very nicely. Something that would be very nice would be to study something like the thermofield double state. So you have two CFTs that are coupled just through the entanglement. In this situation, we expect horizons in the bulk, and it would be fascinating to see if we can learn something about the horizons using this approach to holography. And then I just want to point out that we're trying to make a general statement. So in the vector model, it's very easy to write a complete set of gauge invariant variables. And what we're saying is holography is just a change to gauge invariant variables. So for multi-matrix models, something like n is equal to 4 super-Yang moles, we would suggest the same. Rewrite the conformal field theory in terms of gauge invariant variables. There's a systematic way to do that. It's called collective field theory. The trouble with this, it's a technical problem. Well, maybe there's more, but certainly there is a technical problem. And the technical problem is basically that it's very hard to write down a complete set of gauge invariants. It's very hard to characterize that space. For one matrix models, you can actually do this because the space of gauge invariants is the space of eigenvalues. And when you write down the collective field theory for a single matrix model, you get what's called the Das-Yevitsky string field theory. And we know that this gives you a correct one-dimensional theory of quantum gravity. For multi-matrix models, it's this very first step that we get stuck on. We don't even know how to write down a good set of invariant variables. Thanks for your attention.
Thank you very much for this presentation. So it's time for questions now. So where's the online mode? We ask some questions at this time. So, are there any questions? People in online? Or so Robert, I would just like to ask a question. That
Yes.
is this procedure of bilocal holography in some way going to give a justification for the root pattern and formula for the holographic entanglement? Instead, you are trying to reconstruct the bulk. Can you also give a derivation of the root pattern formula?
I'm sorry, the connection is not very clear. you know, I'm connecting to Google with the VPN because I'm in China at the moment. So that they blocked Google. Can you maybe repeat the question?
Yeah, I'm repeating the question once more. The question
Yes.
is that you are, what I have understood is that you are trying to make a bulk reconstruction by this approach of bilocal holography. So
That's right.
will it be possible to also give a derivation of the youth identity formula in your procedure?
Okay, so that's an excellent question. So I think that it should be possible to derive Ryu Takayanagi, and even more than that, some of these generalizations which were put forward by Wall and Engelhardt. So I think that's a wonderful question. I've been thinking about it. I don't know how to do it, but I think that this is a simple enough example that at least for this case, we should be able to derive the entropy formula.
So are there any more questions? So maybe before we stop, just one more question. What I understood in your approach when you constructed the bilocal fields, you had some fluctuating term which was going as 1 by root n. So there was a 1 by root n correction, 1 by n correction kind of thing. So
that's right.
So is it meaningful to go to higher orders of 1 by n hours?
Yes, in fact, because this is a free CFT, if you tell me how many fields you have in your correlation function, the 1 over n expansion actually truncates. So it's not an infinite expansion. You will have some powers. It doesn't go on forever, at least not for simple correlators.
Okay. And does this expansion, can you make this still expansion work at finite temperatures also? Does it work at finite temperatures also? For a finite temperature CFT, I mean.
Sorry, does it work in what case?
I guess these things you're working at t is equal to 0, right?
No. So this is you know, this is for any time and in 3 dimensions.
I mean CFT at t at temperature at a 0 temperature.
No, it's CFT3. So this is in 3 dimensions.
No, I mean that this expansion that you are making, this is at 0 temperature.
Oh,
so my question is, will it work for finite temperatures also?
Absolutely. So you can study the thermal field double state in this case. That is at finite temperature. One of the things that you find is evanescent modes, which is meant to be a signal of a horizon, but you do not get such a nice picture of the geometry. So at the moment you have some technical results, but you don't really understand the physics of them.
Okay. So if there are no more questions, let's thank the speaker once again for a very nice talk. The next speaker is Kochun Magchi from Kanpur. We shall be talking on tensionless tails, and this is an invited talk for 40 minutes. So, it's all yours now.
All right, thank you very much. A big thank you to the organizers. I had really hoped that this would be the first, offline, conference talk that I would give in a while. But unfortunately, we seem to have circled back to being online, and I'm still sitting at home, not even going to office. But anyway, so let me try and share screen. I hope I'm audible. And
yes, you are audible.
Yeah, and I hope you can see my screen as well. So I will try and make this full screen and hope for the best. And maybe let's see if I can. Sorry, there's this irritating thing about height. Just give me a second. Let me see if I can hide this. Yes, and this. All right, so if, we can start. So this is going to be some entertainment based on stuff that we have been doing of late. And the people, the actors in the play, if you will, are so-called the tensionless people are here. So Orithro, Shankhadeep, and Pulasto, we have been at it for a while. And there are new people here at IIT Kanpur who have joined in the fun as well. I'm not sure if it's fun for them, but it's fun for me. All right, so the main reference for the talk today is going to be, the first one. I'll also talk a little bit about, the paper we put out. I mean, actually, I'm going to talk mainly about the 2019 paper later, and I'll give you an idea of what we are doing. The two start things and as work in the previous direction will be something that the first half of the talk is going to be based on. So you see, we've been at it for a while. And first question is, why are we doing what we're doing? So this is a brief outline of the talk. So I'll start with an introduction, give you some classical analysis, and then move on to quantum aspects of null strings, give you a little bit about applications, and try and conclude. If you do not like my talk, you're free to hand me with the news that you find on the right-hand side of the slides. All right, moving ahead. So firstly, why are we interested in null strings? What are they? Why am I giving this talk at all? So we start off with massless point particles. We all know that these move along null geodesics. World lines are null. So what are null strings? Null strings are supposed to be extended analogs of these point particles. So it's essentially, so whatever masslessness is to point particles will be equivalent to what tensionlessness is to strings. So they have been looked at since Child in the 1970s. So as is very well understood, when we take the tension of the fundamental string to infinity, this is the point particle limit of string theory that gives you, classical gravity, and this is well understood. What we are interested in, however, is the opposite limit, the ultra high energy, ultra quantum limit, if you will. So we want to dial the tension down to 0. So, and why are they useful? So null strings, as I'm just trying to emphasize here, are important for understanding, for example, very quantum gravity. If you want to understand very stringy string theory, this is the limit that you should be looking at. They are of interest for strings at very high temperatures. We'll briefly touch upon the hydron phase later in the talk. They're also of importance for strings near space-time singularities. So if you take strings near black holes, they stretch out, they lose their tension, essentially become tensionless at the horizon. Again, I wanted to say something about it. Hopefully we'll get there at some point. And there are links to high spin theory, which I will not really say much about in this talk. All right. So, very, very brief summary of our results is the following. What happens essentially is that when you're looking, so what we want to do is we want to look at this whole thing from the point of view of the worldsheet. So what happens on the worldsheet is, in usual string theory, you have these two copies of your Virasoro algebra that gives you a two-dimensional CFT. And that is what essentially is at the heart of why we can understand string theory the way we can. What happens is that in this limit, that is going to be replaced by the so-called BMS algebra. And we will use these, the symmetries of the BMS to construct analogous things for the tensionless strings. So the classical ones, I'll show you that you can obtain the properties intrinsically and also as a limit of usual tensile strings. But in the quantum regime, there is a lot of new physics, which I hope to get to, sometime in the middle of the talk. So, there is a very real danger of me meandering. So, please do let me know, if when I'm near the end or so on, I can go on speaking about this for a long time. And also, it will be very much more fun if there are questions in between, so that I don't. Yes, please.
Hi, Arjun. This is Partho.
Hi, Partho. Long time no see.
Long time no see. My first question is, well,
Yes.
maybe the only question,
Yeah.
is that in your massless world, how do
Yes.
you and I exist?
I will say I'm thinking of strings at the moment, and what I wanted to understand, just to get back to it with this of course, how do you generate mass? Is there a symmetry breaking mechanism? All of that is something, does usual string theories come as a, spontaneously broken phase of this, or as an explicitly symmetry breaking phase of this? These are very good things which I do not have an answer to at the moment. What I'm doing, as a very, very first step, is that since we understand massless, point particles in some, in a reasonable way, can we address, tensionless strings in the same way? And are there lessons that we can learn from there? Does it have to, is there new physics there? So I hope I would be able to show you by the end of the talk that there are very interesting structures around which sort of beg the question that we should be trying to address it in this way. But it's just maybe a first few steps in a very, very long program of what we can do with it. I hope to be able to elaborate on this as we go forward. Yeah. So let's start at the beginning, and this is classical null strings. So this the main reference for this is this paper by Isberg et al. In 1994. I revisited it some 9 years back, and I have been sort of working on it from there. And so I'll just take you through the basics of this. Okay, so let's start with the very basics. So we start with the Nabu-Goto action. So there is this t sitting out in front. So it's not a very good idea to take t to 0 because the action is just going to go to 0. So there are generalized momenta. So what we'll do is we'll switch to the Hamiltonian framework. Okay. So once we switch there, then what you can do is, in equation 2, you see by switching, that we have been able to bring tension, which was up, before equation, before the integral in equation 1, into something which has now, gone into the last term in equation 2. So we can happily sort of take the tensionless limit out here. And if we sort of identify G alpha beta as this matrix that we have written out there, so the first thing is that you can now take a tensionless limit, right? So that's one thing. So from equation 2, t going to 0 is something that you can do. But as you can understand, this is a singular limit, and there is something singular that will show up. And it's very clear when you look at this formulation in terms of Polyakov-like action. If you take t going to 0, the determinant of this G alpha beta will go to 0. Okay, so the metric actually is degenerate. So what we need to do is we need to replace this degenerate metric density. Well, what we'll do is we'll replace these by vector densities V alpha. So equation 5, if you wish, can be thought of as the starting point of tensionless strings. You can think of this as think of these tensionless strings as fundamental objects, and you can go from there. All right. Okay. So what is the first part of the talk? The first part of the talk is that I will show you that you can start off with usual tensile string theory. I just showed you that you can go on to tensionless string theory in some way, but you can also then from your tensionless string theory you can go to your favorite thing in tensionless and string theory by an intrinsic method. I'll also show you that there is this other way of trying to close the square, whereby you go from usual tensile string theory to your favorite thing in tensile string theory, and then to this object which you found intrinsic. Okay, so I'll give you a few examples of this as we go along. All right, so let's start with symmetries. Okay, so the tensionless action is invariant under worldsheet diffeomorphisms. So we will need to fix a gauge. So we will fix what's the analog of the conformal gauge. And so let's remember the usual story. The usual story is that when you fix the gauge when you fix conformal gauge in usual tensile string theory, there is still a residual gauge symmetry that is left over. This is 2 copies of the Virasoro algebra, leads to 2D CFT, and is central to understanding string theory. What we'll find here is that in the tensionless case, there is a very similar thing that happens. What is going to be the key is that we will see that the algebra actually has changed. Okay, so so this is a set of worldsheet diffeomorphisms, and going through with the algebra, what I'm going to do is I'm going to make this a little quick. So you will find that this red box equation that you have is the algebra that we find as the residual gauge symmetries of the tensionless string once we have fixed this gauge as V alpha is V0. Okay, so this is the 3-dimensional Bondi-Messner-Sachs algebra, or also known as the 2D Gilliland conformal algebra, has appeared as asymptotic symmetries of 3-dimensional flat spacetime, has arisen in non-relativistic limits, and so on and so forth. And there's a lot of stuff that we know about it these days. Okay, and we are going to use this symmetry algebra over and over again throughout the whole talk. So this is central to understanding it. This problem. Very good. I spoke to you about yes.
So,
yes. Hi, Amitabh.
Hi, Arjun.
Yeah.
So CL and CM at this point, they are free parameters, so the number.
Yeah. That's a good point. I have written CL and CM because they are just things that you can write down out there. This and classical analysis will obviously not give you any idea about what CL and CM are. So we will have to do something else. So when we sort of quantize the theory, it will depend on your choice of vacuum, your ordering of operators, and so on.
Just a question about gauge fixing.
Yes.
And since you're going to deal with massless strings,
yes,
couldn't you formulate in terms of light cone coordinates right from the outset?
We could and we will, but at the moment, what I'm trying to do is sort of build the analog of CFTs. Okay. So we there are obviously as you know, there are plus points of trying to understand things in a light cone gauge, and also there are several things that are more transparent in something like this gauge, right? So conformal gauge is useful when you're thinking about symmetries of the problem. So that's what we will do for now. But we have done light cone analysis, and I can give you a sort of brief flavor of some of the things that we have done. Yeah. All right, good. So now I spoke to you about a limit, right? So let's look at this as a limit. So what we know is you can start off with usual string theory, write down 2 copies of your Virasoro algebra. Remember that if your worldsheet is a cylinder, let's think about closed strings at the moment. Your worldsheet is a cylinder. Then your symmetries are best expressed in terms of these 2D conformal generators on the cylinder. And then what is this tensionless limit? This tensionless limit is the limit where this length of the string actually becomes infinite. We also are thinking about closed strings at the moment. So we also need to have the ends identified. So it's not the greatest idea to take sigma out to infinity. So instead, what we can do is we can rescale the tau parameter. Okay, so we can think of it as the following. So it's sort of like the string that gets stretched. So this was the intuitive idea. How does the algebra make sense? The algebra actually does make sense when we redefine. So the script tells in terms of these flat L's as I have written down up above. And you will see that you can write down now these new vector fields which are well defined in the limit. And these essentially are the same vector fields that we got in the earlier analysis. I rushed through that analysis, but you can sort of take it from me that the analysis actually gives you identical generators, Ln and Mn. Of course, there are details in most of our works. So this is the algebra again, and so what I will just mention sort of fleetingly here is that the tensionless limit on the worldsheet is a sigma going to sigma, tau goes to epsilon tau. So essentially, worldsheet velocities are being scaled to infinity, and essentially the worldsheet speed of light is actually going to 0. This is what is called Carolian limit these days, where weird things happen, like light cones close up, and the worldsheet metric becomes degenerate. So Riemannian structures on the worldsheet, or pseudo-Riemannian structures on the worldsheet, will be replaced by something which is a Carolian structure, which is more like a fiber bundle. Again, I could spend hours trying to speak about this alone, but since we have a long way to go and I wanted to give you an outline of what we are doing, I'll not spend more time over this. But please feel free to ask me more questions about this later. Okay, so another quick thing is, what do we do in usual string theory? So what we start off by quantizing the worldsheet as a theory of free scalar fields, and the constraints are essentially the vanishing of the equations of motion, which here were fixed to be flat. So the operator form of this is the physical states must vanish under the action of the energy momentum tensor. Right. So in this case, I've told you about a limit which makes sense. So let's just see what algebraically this amounts to. So we have written down the so the energy momentum tensor on the cylinder, and if we take the limit as we have done earlier, we'll get these expressions called T1 and T2. I would urge you to keep the expressions in mind. So classically, what we want to do is classical constraints on this tensionless string is going to be T1 is equal to 0 and T2 is equal to 0. The quantum version of this is going to be, when T1 and T2 are sandwiched between physical states, this will be equal to 0. Again, I hope to get back to this, a little later as well. But for the moment, let's focus on the, classical constraints on the string. Now we'll do some very, very sort of straightforward math. Let's go through this. So what do we have? We have equations of, we want to write down equations of motion. It's a very straightforward thing to see that in this gauge, VA as V0, the equations of motion just become x double dot equal to 0. So the solution of this will be of a form that I've just splashed here. And we are looking for closed strings here. So we will have x mu at sigma is equal to x mu at sigma plus 2 pi. So the A naught becomes equal to 0. You can calculate what the constraints are. They would come out to be x dot equal to 0 and x dot x prime equal to 0. Plug in the form of x mu's here, and then you will get these sort of the x dot gives you a b squared, and the x dot x prime gives you an mixture of a's and b's. Okay. What we will do is we will define L's and M's and L's as A dot B's and M's as B dot B's. So once we do that, so the modes are of the form that we had actually derived earlier from purely algebraic, in a purely algebraic way. So this is nice, this is good, and you can obviously do the algebra of the modes. The point to keep in mind here is that AB is not harmonic oscillator. This is actually more like X and T. Okay.
Would you mind just
yes. Yeah, please.
Usually we have the two constraints are pi dot x prime and pi square plus x prime square is equal to 0.
Mm-hmm.
So what I find that one of your constraints is just x dot square is equal to 0. So
that's right.
Easy. So why is this different?
So it is not going to be the same, right? That's the point. So this worldsheet algebra has changed. The worldsheet has changed. It's a very singular thing, right? So it's a singular limit that you have taken. So the constraints on your worldsheet will also change. So in a sense, you can think of this as, think of this sort of tensionless string as a number of just massless point particles, which interestingly also have the memory that it is a string. Okay. So that's the thing that we are trying to deal with. So it will not be the same as usual string theory. Otherwise, we can all go home, right? And it won't be of much use. But this is just that. So constraints have changed. Yes.
Okay, please go ahead.
Yeah, sure. So again, you can look at the algebra of this, and it's again going to close onto the BMS algebra as advertised, and quantization is going to lead you back to what we had earlier. Very good. What we did is we started off with the usual. So we started off with the intrinsic approach. We wrote down what the equations of motion are. We did mode expansions, and we found all of this. As I said, I'll show you how to close the square. So the closing the square is now from, you can start off with the tensile mode expansions, and you can put in appropriate epsilons. So I've labeled this with these red epsilons which are here, and you can systematically take the limit. What I urge you to look at is this box where I relate A's with the alphas and A's and B's with the alphas and alpha tildes. Okay, and once you square them up, you'll recover the thing that we had earlier, that L's and script L's and M's and script L's are related in this way. Okay, so this is the relation between tensionless modes and the tensile modes that we will go back to again and again. All right, so this works. This is great. So this is sort of the place where I can stop and I can ask if you guys have anything more to ask me regarding the classical part of the analysis, because things are going to get more funky from now on.
Just a question, Arjun.
Yes,
what about the spin of the modes? Is there any statement?
That is a very interesting question. I've also not said anything about the mass.
Yes.
It is, so what are the excitations? The expectation is that you are going to get massless higher spins, all over the place. Okay. But it's a little more. So in a way, there's a naive way of seeing it, of course, which I'm sure that you see that straight away. Is that if you take the usual bar squared formula for string theory, and that has a 1 over alpha prime, and if you take alpha prime going to infinity, that just gives you massless higher spin modes all over the place, right? So that's the naive answer. But we will have much more to say about it. So just hold on for a little bit more.
Okay.
All right. So now we want to. So this is going to be work from about 2 years back now. So I'm going to start off with a little bit of BMS representation theory. So there is this important class of representations of three-dimensional BMS, which are called massive modules. These are states of wave functions which are labeled by M0 and L0. This M0 will give you the mass and L0 will give you the spin. And the thing is that all of the MNs acting on these MS, the state function MS, is equal to 0. Okay, so one can use. So this defines this 1D representation, which can be then used to define the induced BMS modules. And notice that we can use all of the L's acting on the wave function MS to build the states. Build the basis vectors of this representation. If we start off with CFT, then as we said, these flat LNs are related to the script LNs in the way that I have shown out here, and so let me just I can't use my pointer, unfortunately, but okay. So let me try and see if I can do this. Just give me a second. Yeah, so the flat LNs are related to this. Is my cursor is visible now? Is it?
Yes, it is.
Yeah. Okay. So these the flat LNs are.
Your cursor is visible. The equations are too small for me.
Okay, I just wanted to point this out. Okay, let me get back to what I was doing. Yeah, this is a curious problem in this full screen mode that you can't see anything here. But okay, so the point essentially is that you start off with the Virasoro and primary conditions, and if you take this, ultra-relativistic, Carroll limit on them as we have been doing, then you will see that this essentially translates to the boxed equation that you have above. Okay, so I have some 33 out here, which I don't know must be a sort of typographical error, but so the point is that when you start off with Virasoro highest weights and you take the limit that I've been trying to speak to you about, then you end up with this, BMS induced representations, which are labeled by L0 and M0, and all the M's acting on this give you 0. Okay, this is the thing that I want you to keep in mind. Okay, moving on. So let's try to so what in terms of oscillator modes. Now all the MNs acting on this state MS is going to be equal to 0. Remember that the M's were squares of B, so M was B into B. And so now what we are going to have is that we are interested in this all these. So we are interested in something which we'll call the vacuum module. And all these BNs acting on it will be equal to 0. Okay. So where am I going with this? Let me just take you back to what my A's and B's were. So let me just remind you of this once more. So remember that my A's and B's were here, right? So my A's and B's were given by the expression here, and the algebra of the A's and B's were like X and B. So what I've done later is now I have changed into something that I'll call C and C tilde, where this is an admixture of A's and B's, and the central point in doing that is that the algebra of the C and C tilde will be harmonic oscillator. Okay. If we write this C and C tilde in terms of the original alpha oscillators, you can see that these are given by a linear combination of alpha n's and alpha tilde minus n's. So for a lot of you, there will be a lot of bells ringing out here, and I urge you to hold on for a few seconds more. But the main point that I want to stress is the oscillator vacuum defined by 0C is not the oscillator vacuum defined by these alphas. Okay, so these two are distinct. And if we want to write this above equation that I wrote earlier as Bn of I equal to 0, if we want to write it in the C language, this is Cn plus C tilde minus n acting on I equal to 0 for all n. So keeping all of this in mind, this last equation is precisely the condition of a Neumann boundary state. And this Neumann boundary state is given by something that I've written down here. Okay. So this is all very standard stuff, but in a minute, this is going to lead you to something which is non-standard. But before that, let's go on to the what a lot of you were anticipating. Of course, the relation between the alphas and the C's are Bogoliubov transformations. These are Bogoliubov transformations on the world sheet. Since they are Bogoliubov transformations on the world sheet, I can relate the two vacua alpha, 0 alpha and 0C. Okay, and in terms of 0C, 0 alpha is a squeezed state. This is essential sort of physics of Bogoliubov transformations that is familiar to all one and all, essentially. But we have these two separate states, two separate ground states, one defined by the alpha oscillators, the other defined by the C oscillators. One is a squeeze state in terms of the other. Okay. What are we going to do now? When epsilon equals to 1, so we can just go back here once more, and we can see what the relation between alphas and C's are. So when you put epsilon equal to 1, I mean tan hyperbolic theta is equal to 0. So 0C and 0 alpha are the same thing. When epsilon will change from 1, from the point of view of the observer C, the vacuum is going to evolve. It is going to become a squeeze state, as we have known before. When epsilon actually goes to 0, which is where we are interested, we'll have tan hyperbolic theta equal to -1, and 0 alpha becomes this state which is exponential of C into C minus n, C tilde minus n acting on C. Where have we seen this before? We have seen this in this induced vacuum that we introduced before. So what is happening? You started off something with something that was a closed string, which was given by the vacuum 0 alpha. We have dialed the tension to 0. And in doing that, what we have found is that the vacuum that we actually go into is given by a Neumann boundary state. So this is an open string which is free to move in all dimensions, or equivalently a space-filling D ring. So just by looking at tensionless limit in a closed string theory, we have obtained an open string. Okay, and the algebra is basically harmonic oscillators and Bogoliubov transformations at the end of the day. Okay, let me pause for a second to hear objections around. All right. If there are no objections.
There are no objections, but just if I have understood correctly, your last statement in the box basically says that a tensionless closed string theory is basically dual to an open string theory with tension.
I'm not, no. So what I'm saying is that firstly, I'm not saying dual. I'm saying that when you start off with tensile closed string and you dial this tension to 0, what you end up with is an emergent open string. So let me show you some pictures. Okay.
But that open string has tension, or is it also tensionless?
No. At the end of the day, when you are, so this is the tensionless limit, right? So it's a tensionless open string.
Okay.
Okay. So this is a sort of picture of it, if you wish. You start off with the closed string. Make the tension less, so it becomes longer and floppier, and more longer and more floppy. Ultimately, there is an emergent open string. So this is one picture, and the other one is that when this can be equivalently thought of as a space-filling D-brane. So what happens is that you have a string, and it's sort of this sort of box that I have with the string is the entire space-time. So it grows and grows and fills up the entire space-time. Okay, so these are sort of two pictures that I want to put before.
Arjun, there could be a third picture which maps the world sheets.
The world sheets, the point essentially, of course you can draw much more, but so the world sheet, what we are trying to actually propose is that the world sheet in this limit is fundamentally different. Fundamentally different as in the structures on the world sheet go from being Riemannian to something else. Okay, the metric degenerates and all sorts of fun starts to happen.
Okay, so it's not the world sheet of a standard open string.
No, it's not.
Okay, great. So that's something new happening.
So let me give you some more pictures and try to needle you guys a little bit more. Okay, so okay, So now, so let's do another very sort of naive analysis. Let's take any sort of perturbative state in usual string theory, okay? And we want to understand how this is going to evolve when we dial this tension down to zero. What I'm going to be doing is I'm going to be looking at it very close to this tensionless point, where I can expand this 0 alpha in a series like, you know, I plus epsilon I1 plus epsilon squared I2 and so on. So just a little bit of algebra, and then what you can do is you can start off with the alpha oscillators on the alpha vacuum, and then you can get some equations for A's and B's acting on the I and I1 and so on. Plug this back in, okay? Plug this back in and look at the any, as I said, any sort of perturbative state in original string theory. Once you do this and you do this little bit of the algebra, you'll see that every perturbative state in your tensile theory, in the limit where tension goes to zero, actually goes to the induced vacuum. Again, this is a very straightforward, algebra out here, which you can do is just 2 lines. So what is happening is all the perturbative states in the closed string actually condense to form this, open string vacuum at the end of the day. Okay. So again, another picture is you start off with the usual string spectrum. You know, once you decrease tension, the spacing decreases, but there's no sort of qualitative change. But at the end of the day, there is something that emerges, which is sort of like a Bose-Einstein condensate of these closed strings, essentially. Bose-Einstein-like, if you wish.
3 minutes more.
I have 3 minutes more, and I have 300 slides more, so that is not going to work. So this is sort of like the end of one part of the story, and I was expecting that I'm going to run out of time. So let me quickly give you a skim through of a few of the other things that I have done. We have been looking at. So it's a lot to go through in 3 minutes, and I don't want to do that. So let me try to give you just a brief idea of stuff. Okay, one of the interesting things, whenever you think of Bogoliubov transformations in physics, one of the things that you naturally think of are Rindler spacetimes. So what you can do is actually, by identifying these Bogoliubov transformations that we have with with usual Rindler Bogoliubov transformations, you can actually recast this decrease of tension on the world sheet as an increase of acceleration of the world sheets. Okay, so the tensionless limit of string theory can be modeled as a series of world sheet observers with increasing acceleration. The tensionless string or the null string emerges where the accelerated observer actually hits the Rindler horizon, which is where the acceleration goes to infinity. This is something that we have made precise in 2 works and more on the way. But again, to leave you with some pictures, this is some pictures of strings with increasing acceleration. So that is that. And again, so there is some more interesting stuff which I could say. One more thing is that you can hit the horizon by accelerating in acceleration. You can hit the horizon by moving in acceleration. You can also hit the horizon by trying to move in Rindler time at constant acceleration. And then, as you can see from the figure down here, what you need to do is you need to take slices of Rindler time on your accelerated world sheet. And then, as you can see, the picture that I drew for you earlier about this, the string becoming longer and floppier and ultimately becoming a line, is something that you get very naturally out of this. Okay, you can make the algebra. You can look at the algebra as well, and everything fits in very well, and you get this emergent null string. Okay, I am literally out of. I maybe have a minute more, so I'll leave you with one more thing.
Yeah, sure.
So yes. Yeah. Okay. So let me just quickly, maybe give you the excuse that you have some I have coffee to drink after this to take one extra minute. So as I said at the beginning, right? So the classical constraints on the string were these T1 and T2 equal to 0. But the quantum version of it was that you have to place these T1s between physical states. So if you place this between physical states, it sort of amounts to this boxed equation which I have out here, and that is going to be, so that is the equation that we need to satisfy. Interestingly, if you have f which satisfies this sandwich equation, there can be three different sorts of solutions, where fn acting on this physical state equal to 0 for n greater than 0. This is the thing that we are all used to. There's another one which you guys saw actually, where fn acting on the physical states equal to 0 for on n, except n equal to 0. And there's a third one, very weird one, where fn acting on the physical states is not 0, but the sandwich actually is. So if you do a careful analysis, it seems that you can have, so there would be not one, not two, but three inequivalent quantum theories that we actually get out of the classical theory that I described to you. So the induced vacuum was the theory that we discussed so far. Then there's something else called the flip vacuum that leads to ambitwistor strings, and there is something called the oscillator vacuum, which is very interesting and has hints of huge underlying gate symmetry. I'll leave you with this last thing. So when you look at light cone analysis and you do critical dimension analysis, you will see that the oscillator vacuum is fine for d equal to 26. Flip vacuum is the same as well. And the induced vacuum does not put any restrictions on d. It's consistent for all dimensions. So all of these can exist as corners of quantum tensile string theory. So I think with that, I'm going to skip all of the rest of the slides, including applications. And so I'll just leave you with a summary of what we have done. Unfortunately, the applications is something that we didn't get to. But thank you a lot for your attention.
Thank you very much. So let's thank the speaker for a very nice.
Yeah, June, very nice talk. Although,
thank you, Badala.
Yeah, but the physics is of course intriguing. But I have a problem which has been bothering me a little bit. So maybe it's a naive issue. You see, when we have a massless field, there are only two possible polarizations classically, and the corresponding quantum field has two helicity states. And often, there are singularities when you try to go to those two polarizations from the massless limit of a massive field, let us say. And this is the old problem of going to Maxwell from Proca. So I was wondering, shouldn't there be a formulation of this which does not have to, you don't have to take the tensionless limit of a tensile string? I mean, couldn't there be?
You're absolutely true. So what we are trying to do is we are trying to do two things. One is exactly what you said. Start off with something, with an action, if you will, and do everything from there. So that's the intrinsic approach.
Right.
Now, the point is that, this is a singular, so the limits are usually singular. So you need to be, very careful about what exactly you do, basically, right? So I have shown you that there exists another way, at least when the classical things that you do can be reproduced by the limit. Whatever you are saying is actually true, because the quantum mechanical theory, as you saw here, right, that I just briefly mentioned, the same classical theory can actually give rise to three of these guys.
Right.
So again, there things like operator ordering will be important. How you're going to regulate things will be important, and so on. So that is, of course, a very detailed thing that we want. I want to understand. But this last thing which I flashed out here. Even so this the analysis that we did out here, the thing that you were saying about the light cone, for example, right? So it's not even clear that the light cone algebra. So in the light cone, the space-time sort of Lorentz algebra will close at all. So the analysis that we did was exactly the thing that you were saying. So we did it from the point of view of the theory which does not assume limits. And then we saw that, yes, it does fit in with D equal. So it may have happened that D was not, 26, but 63, right?
Right.
And then this last thing that I said wouldn't have made sense.
Mm-hmm.
But it
I think
seems like...
No, I am saying that your work is certainly important, because to have the limit go through properly is required, of course. But on the other hand, I think that things would be easier if you would have an ab initio massless way of doing things.
That is right. So we try and do both. We try and do both, basically. So yes.
See, because target space. I mean, if you ask for string vacua, what kind of backgrounds are you admitted? Then you, of course, will be representations of a conformal group in higher dimensions, right? Any dimension.
Yeah, I mean, I'm not even sure that is true. I mean, it may be something else actually. So you need to start off. You need to start off with the worldsheet. You need to look at the equivalent of the beta function equations equal to 0, and that since the structures on the worldsheet have changed. Yeah. So this is something that has to be done, basically. I mean,
well, my guess is you probably Weil gravity rather than Einstein gravity.
I would actually, so one of the things that people have been trying to do is they have been trying to put strings on, Newton-Cartan-like backgrounds, and they have been trying to get equations from that. The first guess would be that this gives you something like that. But at least the slide that I have in front of you at the moment does also seem to say that usual things should also work out. So for example, massless, if you want to go from massive particles to massless particles, you don't necessarily have to go into another space-time, right?
Okay, I find Amitav has also raised a hand, so
yeah, please.
Okay. Arjun, I have one question about your last slide, about this last comment you made about black holes. So you discuss in your talk this setup of taking the tensionless limit.
Mm-hmm.
I wonder if one can set this up dynamically. So you throw a string into a black hole on a radial path.
Okay.
And its tension keeps on decreasing as it goes near the horizon. And do you think this setup, the process that you have, that you have discussed can be dynamically realized?
That is a very interesting thing to ask, actually. So the little bit that we know is this. So this is the slide up here for you. So when you look at strings near horizons of black holes, you can show that the induced metric is such that actually your effective tension goes to 0.
Yeah.
So this is something that you can show. But what you are asking is, of course, a much more involved question, right, Amitav? But it would be wonderful to do that, actually.
Yeah.
So the answer is that I would love to do it, but I don't have a good answer for you yet.
It's Steve, we are already overshooted. So, but Ghulam has also raised.
Okay. So quick question, Arjun.
Hello. How are you?
I'm
long
fine.
time.
A long time. Yes.
Yeah.
So what happened to the predictability of the theory then? If you keep the tension as a variable, sort of.
Predictability. What do you mean?
String theory is supposed to give everything, right?
I'm not trying to give you everything, actually, but okay. So predictability, as in, if you could,
no, maybe let me ask as a businessman, what do I get out of it?
You get the following things. So you get So applications, as in, so one of the things that we don't what we want to address at the end of the day is what happens when strings go near the Big Bang singularity. What happens when strings go near black holes? What happens when you try and probe the Hagedorn phase? So the answer, so what I'm trying to say is that the application wise, this is the stuff that you need to look into, in the sense that you need to look into these I mean, you need to, so you need to look into this sort of very singular limit in order to do that. And what we are trying to do is we were trying to sort of build a formalism which addresses this. I mean, so we are trying to explore, if you wish, the extreme high energy, the extreme quantum, extreme stringy behavior of string theory. And if you wish, a first step, I mean, to trying to address that is this. So predictability, I mean, I don't know. I'm not sure we have got. I mean, we have. I mean, string theory trying to give them masses of electrons yet. I am claiming that I'm not trying to claim anything at all. I'm just trying to say that we are building towards formulation whereby we should be able to address some very interesting questions which are out there. So yeah.
Thanks. But I see the other way around. Actually, it's becoming even more, I mean, so wide. That's the problem I was having. Anyway,
Yeah,
let's, because I think we're running out of time. So.
Yeah, sure. We should go on debating that later on.
Otherwise,
Yeah, thank you
Sunanda
very
will
much.
go mad on me.
Yeah.
Debate can go on. Arjun, thank you very much for a very nice presentation.
Yeah, thank you very much, and I hope to be able to see you guys face to face. I mean, sometime soon.
Sure. Next time we want to have you offline.
Yeah, thank you very much. Thank you. I'll try and stop sharing screen
So,
if I can do that. Yeah.
We shall now. It's a tea break, and we shall meet at 4:25 for the last talk of today.
Thanks.
So it's almost time. Next talk is by Arnav Kundu from Shah Institute of Nuclear Physics, and he shall be talking on RG flows, TFT states, and black holes in ADS. So this is an invited talk of 40 minutes. So, Arnav, we may start.
Hi. Should I try sharing the screen?
Sure.
Okay. You can hear me perfectly well, right?
Yes.
Okay. Thanks. Can you see the screen?
It's coming.
Okay. So now you can, hopefully.
Now we can. Yes.
All right. Okay. So I can't see anybody, but okay, that's fine.
Yeah, you can just wait for a couple of minutes because we are.
Sure. Yeah, just tell me when to begin.
Hang on.
Arnab, for you also it is online.
Ah, yes.
Your office is not very far from this place.
I know. It can be even more ironic sometimes.
Yeah, for sure.
How are things?
Yeah, everything is good.
Good.
So, Arnav, we can start now.
I can start? Okay.
Yeah.
Let me go full screen. Okay, so everything is visible and audible, I assume. Okay, so should I begin?
Sure. Please.
Okay, thanks. Thanks a lot, Nando, and the organizers for organizing this this wonderful conference. So I will be. I'm the last speaker, so I'll not try to take a long time, longer than usual. And what I'll try to tell you is basically some very baby steps that that we are really currently trying to even take. I wouldn't say that we have actually taken the steps yet. That has to do with these terms that appear in the title: RG flows, TFT states, and black holes in ADS. And I will try to explain each of these terms as I go along. And hopefully that would be okay. So I should also mention before I begin that please feel free to interrupt me. It's more important to have more interactions than just me having the information flow in one direction. So okay, so with that, let me begin. So first, well, an acknowledgement to the collaborators and the works that we have been doing in past year and also this year with several friends, students, and collaborators. So Elena, who's a faculty member at UT Austin, Sanjit is her student, and a couple of my students, Ayan and Shumon. So we have what I will be trying to tell you about is mainly based on these two papers. Of course, these numbers don't mean anything, but I've just put it up there, which have some very simple observations. And really, I'll just skip it at that. I don't think we understand it. I don't think we have even begun understanding it. But it seems rather intriguing and perhaps an interesting point of view that could be explained or explored in future. Okay, so a brief outline is of the talk is going to be, I'll start with some motivation and introductory remarks, where of course there will be some sort of big questions. But of course I will not be addressing the big questions directly, but that would be sort of the launching pad. And then I'll try to introduce the various terms that already appear in the title: RG flow, TFT states, and black holes. Well, not all of them I have to explain, but nonetheless, in the premise I need to explain. And then what I mainly want to discuss or tell you about today is some generic, very generic aspects of these RG flows in terms of C theorems and C functions, which we all know and are very familiar to all of us. And in particular, the premise or the framework or sort of perspective would be an attempt to connect them to what is happening inside of a black hole. So that also brings in a lot of questions and caveats, and you can of course question various things, improve upon various things. But as I said, we are trying to take a baby step. That's I think that's a fair statement. So and then I'll try to end with basically some comments, some speculative remarks, and some not so speculative things that we can immediately try out. And in fact, we are trying to look into some of those. So that would be, roughly speaking, the plan of the talk. Okay. So what's the motivation? I think it's a remarkable thing that now I can begin a talk related to black hole by saying that black holes certainly exist in nature, because there are so many direct observations. But of course, I don't need to motivate you further, but just to it's a nice feeling to start with something that actually we can sort of directly measure and so on. But that direct measurements and so on, of course, brings us to a very interesting and rather outstanding problem, which I think is of broad interest to people across disciplines, even, I would say, that what happens exactly inside of a black hole. And this question is related to or tied to many questions in theoretical physics. One particular class of questions are, of course, these conceptual aspects of both classical as well as quantum gravity. About quantum gravity, I'll have very little to say, except it will become clear what I will say later. But of course, very directly related to these are exactly what is happening to the physics at singularity, and in particular, much more generally perhaps, is what is happening to the quantum physics inside of the black hole. That's a fairly generic question that you can ask. And the other question is also that how do we know what is happening inside if we are from the outside? So, or rather, how to access this? So, of course, this generally is an involved problem. It's a difficult problem. Sometimes one doesn't even know how to begin. But in some sense, it becomes easier in holography, which is what I will use. So my entire talk will be completely on very conventional ADS-CFT premise. Okay. Is there any question on this? All right. If not, let me keep going. So what is the sound bite of the thing that I want to talk about today? The very basic statement that I want to make is basically this picture that I have here. So long back, almost 20 years back, these gentlemen or these authors, they considered or they asked a question which is basically the question that I will also try to ask in some way, that where in the boundary theory, in the conventional ADS-CFT framework, where in the boundary theory does one have the information about the black hole interior?
Almost, can you just hide the thing that is appearing in the...
Oh, I'm sorry. Sorry. Hold on. Somehow that entire thing went away.
Take your time.
This is good, right?
Yes, it's fine.
Great. Thanks. Sorry. Okay, great. So the answer they came up with was actually a somewhat of an involved answer, but the basic point was that if you compute a two-point function in this geometry, and basically it's a two-point function in the dual CFT, and it's in the analytic structure of this two-point function, in particular in a certain way of analytic continuing the two-point function, is what knows about the interior of the black hole. Much more recently, less than a couple of years ago, these authors, they actually addressed a similar looking question, but from a slightly different perspective. And the sort of one-line answer of this is that a thermal one-point function also knows about the interior of a black hole in some sense, in some aspects. In particular, you can extract the proper time that an observer takes from the horizon to reach the singularity if you know the thermal one-time function. And over the last year and also this year, I think these authors, they have been writing a couple of very interesting papers where they're arguing that the underlying von Neumann algebra of the quantum field theory, or the dual CFT, is actually what makes the sort of the horizon emerge, and in some sense, the inside of the interior of the horizon also emerge. So our framework or our perspective is going to be some combination of these, but very briefly spoken, or very briefly stated, it's going to be the following: that we do know that in a quantum field theory, or if you have a CFT and then you deform it by an operator, you have an RG flow. An RG flow becomes a flow with respect to an energy scale. And typically you start from an UV and you end up in an IR, for example. The arrow here doesn't really mean anything. And generally what we consider is that the energy is a real valued parameter or physical quantity in the theory. And then once we go from UV to the IR, we just stop. But here in this talk today, I want to actually analytically continue along an orthogonal direction, a transverse direction, which I'll call trans-IR. Basically, what it means is that at this point, once you reach this point, you make your energy purely imaginary, and then you keep going and see what happens. This is the picture from the dual CFT. But in the geometry, the picture is actually somewhat very natural, although this might appear a bit strange at the beginning. Okay. All right. So the first thing is that is the thermophile double state. So let me very briefly say what the state is. The state is defined here. So first of all, you consider a Hilbert space of a doubled quantum mechanical system. It could be a quantum field theory. It could be any quantum mechanical system for that matter. And in that doubled quantum mechanical system, what you construct are these states, which is defined in this way. So you have some Hilbert space, left Hilbert space, some right Hilbert space, and you choose some energy eigenbasis, one for the left, one for the right. You do a tensor product. And then you weight each of these terms with a Boltzmann-like factor, e to the minus beta En by 2, where En is the energy eigenvalue of this n. And beta is a parameter as of now. You don't have to identify this with anything that is physical, but eventually this will be related to the inverse temperature. So just getting ahead of ourselves, we can already call this inverse temperature. Now this is certainly a pure state that I can define. And this pure state has a particularly interesting feature. For example, if you trace out, let's say, the left degrees of freedom of the corresponding density matrix, what you will land up with is a mixed density matrix, which is a thermal, as you can see from the expression itself. It's a completely thermal density matrix. Now, so what happened here was we started with a pure state, and somehow by reducing on one set of degrees of freedom, we got into a thermal state. So going the reverse way, sometimes it's called purification. Given a thermal state, you could imagine constructing a thermophile double state for the corresponding rho beta, and that would be a completely pure state. And this process is sometimes called a purification. Now you might wonder, why am I talking about this particular state? Because after all, in the entire Hilbert space, this is just one single state, and that's somewhat crazy. Because I mean, the entire Hilbert space is a very large. In fact, in quantum field theory, formally an infinite dimensional Hilbert space, and I'm just picking one of them. And so there is absolutely no doubt that this state is extremely special, and the lessons that we learn from it, there is a room for questioning how generic they are in the entire Hilbert space. And so I will not address that question right now, but I just want to give you the disclaimer. One more thing I'll say about this particularly special states is that not only in the context of black holes, these thermophile double states are actually states which people are trying to build in the lab and do experiments with, for example, simple spin systems, cold atoms, and so on and so forth. So it's not completely out of place to talk about these states, and there are motivations why people are interested in that sort of construct. But roughly speaking, this is the state I'm going to talk about. So this is really one state in the entire Hilbert space, but somehow my hope is that I'm learning something which is useful. And there are reasons to believe why that is so, but nonetheless, it's by no stretch of imagination making a claim about any state in the Hilbert space. Okay. All right. Now, what is this? What could your thermal state in holography be? There's a very standard answer to this question. So what you do is you take a black hole in ADS. So this is the Penrose diagram, if you wish. So these are the time-like boundaries on the two sides. These green, sorry, not green, the blue dashed lines are the two horizons, and the red lines are the singularities. This is just a schematic diagram. So this particular Penrose diagram has two boundaries, one on the left, one on the right, and you can imagine two conformal field theories living on them. One is one that I call Cft R and one that I call Cft left, and each of them will have a set of operators and so on and so forth. Let's label them by these indices R and L. So this OR. Sorry, is there a question?
No, please go ahead.
Okay. Okay, great. Great. So there's a set of operators, OR, and set of operators, OL. And as you can see from the picture itself, that if I only consider the operator OR living in this triangle here, it would have no way of knowing what is happening on the left-hand boundary. However, once it crosses the horizon, because the same thing can happen from the left side as well, it will invariably meet the other operator somewhere in the middle. So as long as this operator is outside this horizon, it has no knowledge of the left-hand CFT. However, you cannot stop this object, whatever it is, from falling in through the horizon and inside of it. And once it is inside, it knows about the left-hand side as well. This is one important thing I actually forgot to say. I should have said that the thermophile double state, which is this geometrically for me, is a maximally entangled state. That's actually one very important aspect which you want to keep. And this fact that this operator, once it enters the horizon, knows about the left-hand side, is a manifestation, if you wish, of the fact that these two sides are entangled. But in this case, it happens to be maximally entangled. That's an additional feature. Now, there's one curious thing. Given the definition of the thermophile double state, if you just took, for an arbitrary quantum mechanical system, if you just took a T equal to 0 limit, 0 temperature limit, what you would be left with is a product of two vacuum, because there is an e to the minus beta En suppression. So only the vacuum state will survive. The others will just exponentially damped and they just go away from the entire sum. So it just becomes a product of the two decoupled vacuum. However, in geometry, once you have a horizon, there is no process in classical GR that can get rid of the horizon and give you two decoupled triangles which are connected here. So the main point here is that, well, one observation here is that once entangled, it will always remain entangled. So it will never be two decoupled states, vacuum or otherwise. So the T equal to 0 limit is somewhat subtle in this case, if you want to stay within classical GR. Of course, in the quantum mechanics, you can do this, but this would be, all I'm trying to say is that process, decoupling these two, the thermophile double state into a product of two vacuum state, would have to go away from the classical GR description, which I'm not going to talk about. So that's that. And for the most part of my talk, in fact, almost all of it, will just be statements about classical GR in this space-time, really. There's no quantum mechanics that I'll invoke at any point of time, at least not directly. Okay. All right. So what we know is the following. So given such a thermophile double state, or the classical geometry for that matter, so there's a notion in which, in holography, the radial direction emerges, because you can relate the radial direction in the geometry, which is given by or shown by this black arrow here, for example, as the energy scale in the CFT or the quantum field theory, or the dual quantum field theory. Now, so as you can see from the picture itself, so if I am to just draw the arrow, keep drawing the black arrow, I could just come and end at the bifurcation surface, or it's rather natural to just keep continuing along the vertical direction, which would be along the interior of the black hole. So normally we don't really quite talk about this. What we do in holography is often, especially if we have a thermal state, we start from the boundary, we do whatever RG flow we have to do, and then stop at the horizon, if that's the state we are considering. But here, I actually want to keep the entire picture, in particular, keep track of what is happening inside. Okay. So what is the idea? The idea is rather simple. So you set your boundary values of the fields, and then the fields do whatever they do. They back react on the geometry, and you have your Einstein equations to solve for, and then you just solve for the system, and you find out a space-time, which in this case will keep having the horizon, but the details of the space-time will change. Okay. So roughly speaking, this is the dual picture of the RG flow of a deformed CFT. Now, I should make a couple of clarifying remarks. Here, what I'm talking about is really an RG flow of a state. Now, on the face of it, it's somewhat crazy to talk about that, because as we all know, that RG flow basically integrates out higher and higher energy modes and keeps the lower ones. But if I'm talking about one state, you could think that one state would be assigned to one particular energy scale. And what happens if I reach that energy scale when I have in the integrating out procedure? Then you would expect that you are going to hit a singularity of some sort, because you cannot go beyond that. That's the state itself. You cannot integrate out the entire thing. But there's a way out. If you, instead of taking one state, if you take, for example, the entire a linear combination of let's say some basis states, some energy basis states in the entire Hilbert space, then no matter what you integrate out, there is always something left. And the thermal or the thermophile double state is one particularly such designed state, which keeps all the states in itself. So you can actually sensibly talk about integrating out higher and higher energy modes out of the state itself. But we are here talking about RG flow of a state, not a theory. That's an important distinction. All right. So very basic thing about RG flow. Well, you start with an action of this form, Einstein gravity with some matter field, and typically the matter field will have some. I will be in giving examples. I'll be talking about scalars, but it need not be scalars really. For I mean, many of the intermediate discussions will depend on the scalar field, but the end results will not. So it's a lot easier to write down scalars, so that's why I have them here. So one example, for example, is clearly this kind of a Lagrangian, where you have a potential, and the potential gives rise to some mass for the scalar. And what it means is, to fix this mass is basically fixing the dimension of the deformation. For example, in particular, if I write the mass square as delta times delta minus d, where d is the dimension of the space time in which the CFT is defined, then the deformation is of this form. And depending on whether delta is bigger than d or smaller than d, you would have introduced a relevant or an irrelevant or even a marginal deformation, that sorts of things. So that's completely standard. Now, just very quickly, the canonical example, or perhaps the best understood example in this case, is the RG flow of n equal 4 super Young-Mills theory, in which you have 3 complex adjoint scalars. And what you can do is you can mass deform the theory by giving mass to one of them, which is popularly known, historically was done by Lee and Strassler, so it's known as the Lee-Strassler deformation. And that basically leads you to an infrared very non-trivial interacting infrared fixed point, with n equal 1 supersymmetry. And the geometric part is also known very well. You deal with some n equal 8 gauge supergravity, so it's some complicated potential in general. And you look for critical points of the potential by solving an equation of these sorts. And then what happens is, if you are looking at the right potential with some right simplifications, you will find 2 ADS solutions. One is the n equal 4, the other one is the n equal 1. One which I call ADS UV, the other one is ADS IR. So that's completely standard stuff. So how do you find such a geometry? Well, you foliate, first of all, you write down an ansatz, which is called the domain wall ansatz of the metric, which is written here. And that ansatz, what it does, it foliates the geometry with Minkowski slices, as is obvious from this expression, right? So at each constant row, you have a Minkowski slice, and you could think of this process, this foliation, as literally defining energy slice through your RG flow, and at that particular slice, you have a quantum field theory defined on this base. So this is what I tried to show here in the picture. So each of these rectangular slices are one such Minkowski slice as a function of rho. And in particular, so this is a geometry that can evolve as a function of rho. In particular, if you take, or one solution is when the phi's are constant, for example, is that A is rho over L. It's a linear function of rho, and that's basically just the ADS space-time. Now, there's a question that you can ask already at this level, is that the very intrinsic idea of RG flow is related to an idea of basically measuring number of degrees of freedom at each slice in some sense, right? So whether there's a quantity that you can define which measures number of degrees of freedom at each such Minkowski slices, and the answer is yes. In fact, this is something that was written down almost 10 years back, and it takes this form upon these ansatz basically. So what you can show is that this is indeed a good measure of the degrees of freedom, in the sense that at UV and IR it reproduces, if you have an IR fixed point, that is, it reproduces the right central charges, and also it monotonically decreases along the radial flow. So that's what we know. Now, so roughly speaking, this is what I'm writing here. So just as an example, although, I mean, these arguments are rather generic in the sense that they don't quite depend so much on the details of the potential and so on and so forth, but nonetheless, these inequalities are general, and the inequalities are basically mainly making use of things like null energy conditions and so on. And indeed, what you find is that there is some monotonic function, or rather the function that you define has a monotonic behavior as you keep flowing along the rho direction, for example. And in particular, you can also find fixed points of the flow by solving an equation of this sort. Okay. All right. So here what you do is very similar thing. Now I have gone to a slightly different coordinate system, but that's not really a very big, that's not at all a problem. You can work with, it's just a matter of convenience. You can work with this ansatz. It's a completely analogous ansatz that or rather completely equivalent to what I just wrote down. However, now what I want to do new is that you want to have a black hole in the geometry. In other words, you want to consider an RG flow of the state rather than the theory itself. Previously, there was no state. It was just a vacuum state, which was going through the flow. Now I want to consider a thermal state. So you do that. You choose, let's say, a potential of this sort with appropriately tuned m square, value of m square such that the deformation is a relevant one. Then you have some equations of motion. These are classical equations, and it so happens that in these cases you have to solve them numerically given the boundary conditions, and you do that. So you can solve it, but there's one important thing I want to quickly say is that there are two limits where you know everything sort of analytically, and the two limits, one is the boundary, one is the UV data where R goes to 0. In fact, I should have mentioned it here. So near the boundary, you basically feed in this data, the behavior of the metric functions of this sort and the behavior of the scalar as a power of R and so on. And that basically picks out for you what the details of the deformation that you are introducing to the CFT. So these define that. And what comes out from the equations of motion is that near the singularity, this is inside the black hole, near the singularity, you get a Kasner type universe, as you would recall here. So this tau I have redefined in terms of R. And remember, once you are inside the black hole, the radial coordinate now has become the time-like coordinate. So now this is really time, if I look at the metric locally. And this is a cosmological universe, in particular a Kasner universe. And these are exponents, Pt, Px, and P5, which characterize these Kasner exponents. And they also satisfy some equation, which basically just tells you that there is only one free parameter. And that's that. Okay? All right. So this is just one example of a flow. So as I said, this is a sort of caricature, what you do to the flow geometry or to induce the flow. But then you can construct the numerical flows also, or the solutions also. For example, what you read off is one such infrared data, which is one such exponent, this Pt, as a function of the deformation parameter. And the deformation parameter you have to measure in some units. Here we have chosen to sort of normalize it with in units of the temperature itself. So I don't want to say too much about it, although there are some interesting observations that you can make. But let me move on. This is just to state that you can do it. And in particular, so let's focus on one particularly simple case. Namely, when you have no scalar deformation turned on at all. So we know then what we have there is basically just the ADS space, ADS Schwarzschild black hole. And that you can characterize the inside of it, in particular the near singularity behavior, as basically a set of exponents which take these values. And then you can ask, can I write down a thermal A function, quote unquote, thermal A function, which will actually count the degrees of freedom for such a state, which is the ADA-Schwarzschild state. Now, if you tried the previous answer, which had some expression, you would see that it doesn't quite make sense, in the sense that here, of course, what we are looking at is just a thermophile double state of the CFT. We have not introduced any deformation at all. So the degrees of freedom should not be changing as a function of energy. Nothing is changing as a function of energy. So there is one way to achieve that. If you define a function of this type, so this is purely based on, it's not a covariant expression. I'm just giving you expressions in terms of the metric functions. That is okay. So if you define this function and you plug it back some explicit analytic forms of this A and F, you will see that this thermal A function will basically just reproduce the NC square that you want. So it's a constant as a function of flow, and it's just what you would expect, namely the central charge of the CFT itself. Now, you want to make the following statement. Now you want to make the statement that I will actually look at this function itself, which I have again rewritten here in this R coordinate. Sorry if that confuses you, but basically the point is that the R and the rho coordinates are just some coordinate transformation, nothing really going on there. And then what you can do is you can take your exterior of the black hole and interior of the black hole separately, and by using the same null energy condition, you can show that the null energy condition in the exterior boils down to a monotonic condition of this sort, and in the interior it also boils down to a monotonic condition of this sort, where rho and kappa, if you're going inside, rho and kappa are related by analytic continuation. In other words, inside of the black hole is related by analytically continuing the rho coordinate as well as the time coordinate, which I have here. And this is really the energy scale, as you see from the dual CFT. So this sort of justifies the picture that I showed you at the beginning, which was that you have an energy scale, and the energy scale, the RG flow is happening through the energy scale. But then at some point, for some reason, let's say I want to take an analytic continuation of the RG scale. The point here is that you go inside of the black hole in these cases, and then something is also strictly monotonic, even in the interior. So outside, we understand what this monotonicity should mean as we are integrating out more and more degrees of freedom. We would expect that the measure of number of degrees of freedom would be decreasing. But inside, there is no such statement a priori existing, right? But here, based on very simple observations and rather assumptions, you do have that particular structure intact. So how much time do I have right now? Depending on, I guess I'll pace myself. So if you can, Sunando, if you can. Hello.
You have 8 minutes.
I have 8 minutes. Oh, excellent. Okay, I have more than I thought. Okay, great. All right. So let me just okay. So this is an abstract. Well, not abstract, but this is an argument. This is a generic argument. But you can, of course, here solve these cases for these geometries explicitly. And in particular, you choose your potential, you fit in your boundary data, and then you just solve for it. And if you do that, what you will find is for example, one particular class of solutions for which this thermal A function I have represented here, which is just some numerical plot. And this, as you can see, that the blue horizontal line is basically the one that corresponds to no deformation whatsoever. So there, you don't expect the number of degrees of freedom count to change at all, and it doesn't. That's perfectly fine. But now, once you start increasing your deformation, this A function starts flowing, but it keeps a monotonicity, as you can obviously see from the picture. It's clear from the derivation, and I should re-emphasize at this point that the derivation does not depend on whether you picked a scalar field or any other field. It's just as long as you have a stress tensor which has just simple null energy condition, this is guaranteed to have. Now, guaranteed to happen. Now, One thing that I want your attention to be drawn to is the fact that the A function seems to be going to 0 as you go deeper and deeper into the interior and closer to the singularity. And in fact, this does happen. This is something that you can analytically argue. So so that's that. And just for demarcation, this horizontal black dashed line is basically the location of the horizon. So clearly this is outside, the left is outside, the right is inside, and the A function is going to 0. All right. So there is one other example that you can do. The example that I just showed you was somewhat of a really toy model, because I'm just cherry picking my potential without telling you what theory it is and assuming that there is such a theory and indeed everything is fine. But you can, if you want, you can make it much more precise. You can really choose for example, this particular least Strasser flow, for which the explicit potential is known. It's a bit complicated, but you can do it, and you can run the entire machinery through. It works perfectly fine. And then at the end of the day, what you do get is that because now you have both a UV CFT and an IR CFT, somehow the IR CFT always remains hidden by the horizon. But you can fine-tune the system in such a way that the IR fixed point, the so-called IR fixed point, approaches the horizon from inside, very, very close, but it cannot really sit on top of the horizon. So in some sense, the horizon always shields the IR fixed point, which is not surprising really, but it does that. And that is something that you can also track by looking at the behavior of this A function, which I just showed you. So one-line summary of this slide could be that the IR fixed point sort of, as I said already, it remains hidden by the horizon that we have here. Okay. So now comes the question that you can ask, okay, fine, all right, so you decided to go along, this imaginary energy direction or the time-like direction inside of the black hole, but all right, fine, what does that really mean? How would I ever think about extracting information along this line from a boundary observer's point of view? Now, there's already some problem with it. So let me first look at, for some reason, I will not really motivate this part that much because the results are also not that sharp, but I'll tell you what is roughly speaking going on. You could compute various extremal codimension extremal surfaces. And in particular, for example, if you think about codimension 1 and codimension 2 extremal surfaces, which are anchored at the two boundaries, for example, so their minimal point, for example, which is shown by this blue circle here, or denoted by RC here, can only go up to a distance close to the singularity. In other words, said in a different way, no matter where I anchored them at the boundary, I will never be able to access the singularity or reach near the singularity by considering these extremal area surfaces. Now, why do I want to consider them? Because, as you might know already, which I have not reviewed here, entanglement, if you are going to compute entanglement or, for example, complexity of some form, then these are the surfaces that you actually have to compute. So the slogan is, one-line summary of this statement is that if you are only worried about entanglement and complexity as per the complexity volume proposal, that's not going to be able to track the flow of this A function along the entire inside of the black hole, or along the entire interior. So there has to be something else. And the something else is rather simple, actually. So you go back and you look at your two-point function. So for example, on the left, I have shown here. So if you compute, let's say, a two-point function, you also compute, you also anchor basically a geodesic at the two boundaries, and then you vary your boundary time. If you do that, your geodesics will start going deeper and deeper in the interior, and these yellow circles, for example, are showing what they do. And in fact, for this small change here, by choosing TB within this range from 0 to TC, you can actually access the minimal point of the geodesic, can actually access the entire axis that goes from the bifurcation surface all the way to the singularity. So you may ask, what is happening beyond this? Well, how can I map the boundary time to a direction inside of the interior of the black hole? The answer here in this picture is incomplete because it says that I can map the entire interior of the black hole within this range. So what happens outside of it? Now there's the picture will automatically tell you what we have to do, because here you see that this blue circle that is on the singularity is almost actually a null ray. So what you would do afterwards is only consider null rays and basically pick your boundary time and send null rays from there, which is essentially the right picture. So in the right hand picture, if you choose any boundary time which is bigger or equal to Tc, you basically pick your boundary time and send your null rays, and they will meet somewhere inside. And that inside will explore the entire direction, all the way from singularity to the bifurcation surface, or vice versa. And these are the Wheeler-DeWitt patches, as you all know very well. So there's a reason why I'm showing you these pictures, but not telling you exactly what quantity I'm computing. The reason is that, well, Wheeler-DeWitt patches are very closely related to also this notion of complexity, but I don't really have a clear formula to give you that tells you that this is the quantity that you compute as a correlation function or whatever, which gives you this A function. But what I can tell you is what might, for example, because these calculations are slightly involved and one has to check, which is what we are kind of trying to do right now. Sorry?
The time is up.
Yes. Okay, so let me conclude. So as I tried to argue that these trans-IR flows are rather natural in describing the black hole interior, it's really a very basic statement that you take your classical geometry seriously, whatever you have, you take that seriously and go with it. The point is that the monotonic A function does exist, and as I said, based on very minimal assumptions, so it's hard to think of why that would be wrong, for example. It also is consistent with sort of the slogan that entanglement is not enough, because as I argued that if you only care about entanglement, you will not be able to see the entire flow of this A function, of this function from the boundary. Now, it's very intriguing to wonder about whether it has any connection with the mirror operators, operator construction, or some more recent construction in terms of this von Neumann algebra and so on. That's sort of what we are trying to understand in a little better. But of course, one thing is that, I mean, immediately the things that you can do is to try and understand this a little better in terms of, for example, explicitly working out, although that will involve some amount of tedious work, computation, exactly whether there's a relation between or what relation between the complexity and the A function holds, and what exactly it is that you're computing at the boundary, which is giving you this monotonic behavior. And then finally, one comment I want to make is that this analytic continuation of RG flow in quantum field theory, as far as I know, has not really been explored. And it's a generic question whether that has any lessons for us. In particular, the RG equations, if you just look at quantum field theory equations and do this analytic continuation, seems like some de Sitter-like physics is going on. So there might be something interesting from a broader perspective as well. But of course, I'm not giving you the answer, for example, which we do not know at this point, that what exactly it is that we are doing to the state along the trans-IR flow. But it is something intriguing is happening. So with that, I'll thank you with both in real and imaginary directions. So thanks a lot for listening.
Thank you very much, Arnav. So it's time for questions now.
Let me minimize it.
Okay, Arnab, I have one question. So can you go to this slide where you had this answers with the chi function?
Yes. This one?
Yeah. So are you assuming that the f function remains the same and you're only solving for the chi function?
No.
F also changes?
Everything changes. I'm solving these equations.
Oh, so...
In fact, f is actually changing.
So the black hole changes. And then how do you impose the horizon is somewhere when the f function becomes 0?
Right.
And you impose smoothness across that function.
Right.
Is that part of the boundary condition, or that is
part of the boundary condition when you are actually numerically solving it. But as a general, these equations of motion are smooth along at a slice where f vanishes.
Usually, this chi is a back reaction kind of thing, right?
Everything is back reacted here, not just chi. So this f function, as I was saying, that this f function itself also knows about what phi you have excited. Is that making sense?
Yeah. No, it makes sense. Yeah.
So for example, one thing I did not mention is that this story is fairly generic, I suspect, because as you know that, so what is being done here is really simple. Outside the horizon, of course, you have this static geometry that we know and love, like Schwarzschild, but inside you have a cosmology. That's nothing new, right? I mean, that's known.
Yeah.
Now, once you have a cosmology, of course, the cosmological singularities have a classification. I mean, like, for example, you can have a PKL type behavior.
Yeah.
And you can argue that if you have, all you really need is a PKL structure for most of the things that I said to be true.
Yeah.
Hi, Arnob.
Hi.
Good to see you.
Good to see you too. Well, although I cannot see you probably.
Yeah, I was trying to switch something on, but yeah, hello. Yeah, so one quick thing to ask you is everything is smooth. I mean, across R equal to RH, right?
Yes.
Do you naturally expect that to be true for? For all solutions? I mean, wouldn't you expect that? You were saying something that you can move the. One of the fixed points as close as you. Can to R equal to RH, but you can't. Go across with it, right?
No. So there are two things. One is that the smoothness is imposed by hand in the sense. It's smooth in the sense that, okay, if you take GR equations, there can also always be non-smooth solutions, but that we discard, right? So all I'm talking about is just plain garden varieties, smooth classical solutions of GR. Really, at the end of the day, there's nothing more fancy than that. No quantum mechanics going on in the geometry, for example. So if you have any non-smooth thing, you basically discard that. The thing that I'm doing, which is not usually done normally, is to take the inside of the classical solution seriously. Literally, rather, not seriously, even literally. So just to declare that the inside is what it is, that the Schwarzschild metric describes, and I'm not going to change it. I will just construct a broader class of such solutions where the inside has some back reaction and so on and so forth. But then it has some interesting interpretation in terms of something that I can write. So this is roughly speaking what is going on. Now, what you can do, and in fact, it's an interesting question, is suppose now you want to say that there is some small amount of quantum mechanics going on inside. You have some quantum field and you are quantizing it in some ways. You can do that because we do quantum field theory in de Sitter or cosmological scenario all the time. Some version of that you could do, and you could ask whether that makes the structure stable, whether the structure goes away, what happens to this entire classical story. That I do not know.
So I'm just sort of thinking about it from the point of view of suppose you were thinking about CFTs which live inside in each slice, right?
No, that's not what I'm trying to think of.
Okay.
In fact,
if you did, then I would be a little I'm not entirely sure about how you are going to go from the outside. I would expect that you would be able to go as close to R equal to RH from both sides, but somehow something should show up at the null surface.
So yes. So I think it's probably incorrect to think or to try to think of the interior as slices on which a CFT lives.
Okay.
Simply because in this case I can actually make it precise. In this case, you can actually write down a Wilsonian effective theory or how the coupling constant, for example, run as a function of the RG, starting from the boundary, which is where everything is well defined.
Right.
Now, if you do that, you will find out that the coupling constant diverges once you reach the horizon.
Okay.
So that is a clear signature that you should really stop there, or even earlier probably. Now you could still say that, okay, I don't care, I will force it to continue inside. But then it's a very odd thing to do, because Wilsonian sense literally says that if you have a quantum field theory, you define a cutoff, you integrate out what's above that cutoff, keep whatever is inside, keep whatever is below that cutoff.
Below the cutoff. Yeah.
But once you are inside the black hole, what you are trying to do is you're trying to make a statement in terms of energy, not in terms of energy, but in terms of how fast something is moving. That's not the same thing. When you have dynamics, you don't integrate out fast modes and keep slow modes and get an effective theory, sensible effective theory. That doesn't happen. So slicing cannot be thought of, I think, in any practical sense as something on which you want to write down a theory.
Okay.
It would be some very
yeah, that makes sense, I guess. Yeah. All right. Thank you.
Sure.
Hi, Arnav, can I ask a question?
Yes, of course.
Is there time or should I? Okay, so I want to ask a very naive question, actually. See, if you take you have anti de Sitter Schwarzschild, right? That's your geometry, and the Weil tensor outside is non-zero, right? As it must be. Now the Weil curvature tensor, I mean. Now usually, what people do is when they consider the inside in terms of cosmological solution, they take a scale invariant cosmology. So the Weil tensor actually vanishes. And so at the horizon, one has this problem that the Weil tensor is non-zero outside and zero inside. Because if you take a scale invariant, a Weil invariant cosmological solution like a Friedman-Robertson-Walker, then the Weil tensor is zero for that metric, right? So I was wondering, what would the boundary theory say in this case about the Weil tensor?
So this I did not. I mean, this is something that we can actually check just by basically
right. I was wondering.
Yes. And I think since the geometry is smooth, nothing remarkable should really happen. But I'm also not sure about whether the Weil tensor is zero in the interior, because I mean, you see, the interior is not a simple thing like Robertson-Walker. It's not really FRW. It's much more complicated. Once you go close to the singularity, then things become very simple and becomes Kasna.
Right.
So, but that's the limit.
So the Weil tensor would evolve in some ways, and it would be interesting to find out what that evolution is, right?
Okay.
Because the Weil tensor is the real effect of classical gravity. I mean, that's the real thing, which is not related to matter at all, right?
I see. I understand what you're saying.
This is the Penrose.
Okay.
Okay. Yeah. Okay. Great. Thanks very much.
I understand. This is not something we have actually explicitly computed, I think, but yeah, this is something that can be done. Thanks.
Great. Yeah.
Okay. So there are no more questions. So let's thank the speaker once more. All the speakers in this section.
Thank you. Thanks a lot.
Of this day, the first day of the conference. So tomorrow we shall start from 10:30. The first talk is at 10:30. Tomorrow is quite a long day. There are 11 talks tomorrow. We shall meet at 10:30. So bye for today.